microcosm.
Will you answer? The answer should always be yes, because there are more paradoxes to explore, more mysteries waiting in the shadows of our understanding. Let me take you deeper. Quantum teleportation sounds like science fiction, but it's real. We've done it in labs, teleporting quantum states from one location to another. But here's the catch. You're not teleporting matter or energy. You're teleporting information, the quantum state itself. And you can't do it faster than light. You need a classical communication channel to complete the process, and that travels at light speed or slower. So what's being teleported? The essence of the particle, its quantum properties, everything that makes it what it is, but not the particle itself. The original is destroyed during measurement, and the information is used to reconstruct an exact copy at the destination. Ship of Theseus on a quantum level. Is the copy the same particle? Philosophically, we don't know. Physically, quantum mechanics says they're indistinguishable, which means they're identical. This has implications for computing, for cryptography, for fundamental physics. If you can teleport quantum states, you can build quantum networks, quantum internet, systems that are fundamentally more secure and powerful than anything classical physics allows. We're on the verge of this technology. Within decades, we might have quantum communication networks spanning continents, maybe even planets. But it raises questions. If consciousness is a quantum state, can it be teleported? Can you upload a mind, transmit it, download it into a new substrate? Most physicists say no, consciousness is too complex, too entangled with its physical substrate. But some say maybe, and that maybe is enough to keep philosophers and neuroscientists arguing for generations. Here's something that troubles me deeply: the fine structure constant. It's a dimensionless number, about 1/137, that appears throughout physics. It determines the strength of electromagnetic interactions, the spacing of atomic energy levels, the opacity of matter to light. It's fundamental, and we have no idea why it has the value it does. Paul Dirac spent years obsessed with 137, trying to derive it from first principles. He failed. Richard Feynman called it one of the greatest damn mysteries of physics. We can measure it to extraordinary precision, but we can't explain it. It's a parameter we have to put into our theories by hand, taken from experiment, not derived from deeper principles. And here's the disturbing part. If the fine structure constant were slightly different, chemistry wouldn't work. Stars wouldn't shine the same way. Life couldn't exist. Change it by a few percent and carbon becomes unstable. Change it more and atoms don't form. The universe would be sterile, empty, dead. Is this fine-tuning coincidence? Necessity? Design? Anthropic selection from a multiverse? We don't know. And the fine structure constant is just one of about 30 parameters in the standard model, all of which seem arbitrary, all of which seem fine-tuned for life. It's called the landscape problem, and it's one of the deepest issues in theoretical physics. Some hope that a theory of everything will explain these parameters, will show they couldn't be anything else. String theory tried this and found the opposite. A landscape of 10 to 500 possible universes, each with different parameters. No unique prediction, no way to single out our universe from the vast possibilities. Maybe that's the answer. Maybe we live in a multiverse, and the parameters are environmental, like the temperature or the altitude. Different universes have different values, and we're in one where they permit complexity. But this explanation feels like giving up, like saying anything goes, and abandoning the search for deeper understanding. Let me tell you about quantum decoherence more carefully. It's the process by which quantum superpositions disappear, seemingly collapsing into definite states. But it's not really collapse. It's entanglement with the environment. When a quantum system interacts with its surroundings, information leaks out, spreading into countless degrees of freedom that you can't track. The superposition is still there, mathematically, but it's invisible, inaccessible, for all practical purposes gone. This solves the measurement problem, sort of. You don't need a special collapse mechanism or conscious observers. Decoherence happens automatically, inevitably, whenever systems interact. The quantum world becomes classical naturally through environmental interaction. But it doesn't fully solve the problem. Decoherence explains why we don't see macroscopic superpositions, why Schrödinger's cat is either alive or dead, not both. But it doesn't explain which outcome occurs, why you see the cat alive rather than dead on any particular observation. That's still random, governed by the Born rule, and the Born rule is postulated, not derived. Moreover, decoherence doesn't eliminate the other branches of the wave function. In the many worlds interpretation, they still exist, just decohered from each other, separate worlds that can't communicate. In other interpretations, they're somehow suppressed or eliminated, but the mechanism is unclear. Decoherence is progress, but it's not the final answer. The measurement problem persists, lurking beneath the surface, waiting for a deeper theory to resolve it. Now let's discuss something truly bizarre: quantum contextuality. In classical physics, properties exist independently of measurement. A coin is either heads or tails, whether you look at it or not. But in quantum mechanics, this isn't true. The result of a measurement depends on what other measurements you perform on the context. The Katchenspeker theorem proves this mathematically. You can't assign definite values to all quantum observables simultaneously in a way that's consistent with experiments. The properties don't exist until measured, and which properties exist depends on what you measure. This is deeper than uncertainty. Uncertainty says you can't know position and momentum simultaneously. Contextuality says they don't exist simultaneously. Reality is contextual, dependent on observation, relative to measurement choices. Some interpret this as evidence that reality is fundamentally informational, that physical properties are answers to questions we ask nature, not intrinsic features of objects. This connects to Wheeler's it from bit hypothesis. All of physics ultimately reduces to yes or no questions, to information, and matter and energy are derived concepts. If this is right, then the universe is not a collection of things but a network of relationships, of correlations, of information flows. Objects are secondary, emergent from the patterns of questions and answers, measurements and outcomes. This is profoundly weird, and most physicists try not to think about it too hard. We use quantum mechanics, we apply it, we build technology with it. But the foundational questions, what it means, what it says about reality, those remain open, hotly debated, unresolved. Here's a cosmic paradox that gets overlooked: the problem of cosmic rays and the knee. The cosmic ray spectrum, the distribution of particles by energy, follows a power law for most energies. But around 10 to 15 electron volts, there's a break, a steepening called the knee. Above the knee, cosmic rays become rarer, and the spectrum drops faster. What causes the knee? Maybe it's the maximum energy that supernova remnants can accelerate particles to. Above this energy, cosmic rays escape the galaxy before being accelerated further, so we see fewer of them. But the details don't quite work. The knee is sharper than models predict, and its position varies with particle type. Maybe there are multiple components, different sources contributing at different energies. Maybe pulsars, magnetars, or other exotic sources take over above the knee. Maybe cosmic rays at these energies are heavy nuclei, not protons, and they fragment differently when hitting the atmosphere. We don't know. The knee sits there, in the cosmic ray spectrum, unexplained, a reminder that even century-old fields like cosmic ray physics still hold surprises. And beyond the knee is the ankle, around 10 to 18 electron volts, where the spectrum flattens. This might mark the transition from galactic to extragalactic cosmic rays, from sources in the Milky Way to sources in other galaxies. But again, the details are murky. Every feature in the cosmic ray spectrum is a clue to astrophysical processes we don't fully understand. And the highest energy cosmic rays, above 10 to 20 electron volts, those are still completely mysterious, as I mentioned before. Let's talk about the electroweak epoch, the brief period in the early universe, around 10 to 12 seconds after the Big Bang, when the electromagnetic and weak forces were unified. At these temperatures, around 10 to 15 Kelvin, the Higgs field hadn't yet acquired a non-zero value. Particles were massless, zipping around at light speed. Then the universe cooled, and the Higgs field underwent a phase transition, settling into a non-zero value, breaking the electroweak symmetry. Particles acquired mass, the weak force became short-range, and the universe changed fundamentally. This phase transition might have been first order, like water freezing, with bubbles of the new phase nucleating and expanding, colliding, releasing energy. Or it might have been second order, smooth, without bubbles. Current understanding, based on Higgs measurements, suggests it was smooth, but there's uncertainty. If it was first order, the transition might have produced gravitational waves, a stochastic background detectable by future space-based detectors. It might have generated magnetic fields, seeds for the galactic fields we see today. It might have contributed to the baryon asymmetry, creating more matter than antimatter through processes at bubble walls. We're trying to reconstruct what happened using particle physics experiments, cosmological observations, theoretical models. It's cosmic archaeology, digging into the first microseconds, trying to understand the conditions, the processes, the outcomes. And every phase transition in the early universe is similar. The quark-hadron transition at 10 to 5 seconds, when quarks confined into protons and neutrons. The neutrino decoupling at 1 second, when neutrinos stopped interacting and started free-streaming. Each one changed the universe, set the stage for the next era. Understanding these transitions is understanding cosmic history, the sequence of events that led from the Big Bang to the universe we see today. Here's a mystery closer to home: Jupiter's core. For decades, we thought Jupiter had a small rocky core, maybe 10 Earth masses, surrounded by metallic hydrogen, surrounded by molecular hydrogen, surrounded by an atmosphere. Neat, simple, layered. But Juno, the spacecraft currently orbiting Jupiter, found something different. Gravity measurements suggest the core is fuzzy, diluted, not compact. Either the core is much larger than expected, or it's partially dissolved, mixed with the surrounding hydrogen. Something happened, maybe a giant impact early in Jupiter's history, that disrupted the core. This changes our understanding of planetary formation. If Jupiter's core isn't compact, if giant impacts can disrupt cores, then the process of building planets is more violent, more chaotic than we thought. Planets are not serene accumulations of material. They're battlegrounds, smashing together, tearing each other apart, sometimes surviving, sometimes not. And Jupiter's interior is still mysterious. We don't have a good equation of state for hydrogen at the pressures and temperatures in Jupiter's depths. We don't know exactly where molecular hydrogen transitions to metallic hydrogen. We don't know the composition of the core. if it exists as a distinct entity at all. Jupiter is in our solar system and we've sent spacecraft to it, and we still don't fully understand its interior. That's humbling. Now consider quantum tunneling in more detail. It's not just about particles passing through barriers. It's about the nature of possibility in quantum mechanics. Before measurement, a particle doesn't have a definite position. It has a wave function spread out in space with amplitudes in regions separated by barriers. When the wave function has amplitude on both sides of a barrier, there's a probability of finding the particle on either side. This isn't the particle traveling through the barrier. It's the particle being on both sides probabilistically until measurement localizes it. Tunneling is central to quantum field theory, to particle creation and annihilation. Virtual particles tunnel through energy barriers, borrowing energy from the vacuum. Hawking radiation involves tunneling through the gravitational barrier of the event horizon. Alpha decay is tunneling through the nuclear potential well. But tunneling has paradoxical features. The tunneling time, how long a particle spends inside a barrier, is controversial. Some calculations give 0 time. Others give imaginary time, which is nonsensical. Others give finite time, but the meaning is unclear because you can't measure position inside the barrier without disturbing the system. This is related to the measurement problem again. In quantum mechanics, observables don't have values until measured, and measurement disturbs the system. You can't ask what the particle was doing inside the barrier because asking changes what happens. Quantum mechanics is a theory of measurement outcomes, not of underlying reality. And tunneling is a perfect example of why this is frustrating. We have a mathematical description that makes predictions, but no clear picture of what's happening, no narrative, no mechanism. Let's discuss something that sounds esoteric but is deeply important: gauge symmetry. The laws of physics are symmetric under certain transformations called gauge transformations. These symmetries aren't like rotational symmetry, where the physics looks the same if you rotate your coordinate system. Gauge symmetries are internal, abstract, related to the phases of quantum fields. The electromagnetic force arises from a gauge symmetry called U1. The weak and strong forces arise from larger gauge symmetries, SU2 and SU3. These symmetries aren't just mathematical curiosities. They determine the structure of the standard model, the particles that exist, the forces they experience. Gauge symmetries are beautiful, elegant, powerful. They constrain theories, reducing arbitrariness. They connect seemingly unrelated phenomena. They unify forces. But here's the puzzle. Why these gauge symmetries?
Vaju 1, Xu 2, Xu 3.
Why not something else? Grand unified theories propose that these symmetries are fragments of a larger symmetry that broke at high energies. But which larger symmetry? SU 5? So 10? 8? We don't know. And gauge symmetries lead to deep problems. The strong CP problem, which I mentioned, arises because the gauge symmetry allows a term that violates CP but isn't observed. The hierarchy problem arises because gauge symmetries don't protect the Higgs mass from quantum corrections. Gauge symmetries are at the heart of modern physics, but they raise as many questions as they answer. Here's another one, the lithium-7 problem. Big Bang nucleosynthesis predicts specific abundances of light elements: hydrogen, helium, deuterium, lithium. The predictions for hydrogen, helium, and deuterium match observations beautifully. But lithium-7 is off by a factor of 3. Old stars, which formed early in the universe and preserve the primordial composition, have about a third the lithium-7 that models predict. Where did it go? Did stellar processes destroy it? But models of stellar evolution can't account for this much depletion. Maybe the nuclear reaction rates are wrong. We've measured them in labs, but maybe at the temperatures of Big Bang nucleosynthesis, something different happens. Maybe resonances we don't know about alter the rates. Or maybe new physics at a few minutes after the Big Bang. A decaying particle not in the standard model that affected nucleosynthesis. Or a different expansion rate altering the conditions. Or primordial magnetic fields changing the electron-to-baryon ratio. These solutions are speculative, but the lithium problem is real. It's a crack in Big Bang nucleosynthesis, one of the foundational pillars of cosmology. And cracks spread. Let me tell you about the neutrino mass hierarchy problem. We know neutrinos have mass. We know there are 3 types, but we don't know the order of the masses. Are they arranged like 1, 2, 3 called normal hierarchy? Or like 3, 1, 2 called inverted hierarchy? The mass differences are known, but the absolute ordering isn't. This matters for understanding neutrino oscillations, for detecting neutrinoless double beta decay, for constraining the absolute mass scale. It matters for cosmology because neutrino mass affects structure formation. Experiments are trying to determine the hierarchy by measuring neutrinos from reactors, accelerators, the atmosphere, the sun. The data is accumulating and it slightly favors normal hierarchy. But it's not definitive yet. And there's a deeper question. Why are neutrino masses so small? The electron mass is about 500 keV. The top quark mass is 173 GeV. Neutrino masses are less than 0.1 electron volts, a billion times smaller than the electron. Why? The seesaw mechanism offers an explanation. If there are heavy right-handed neutrinos, they can give small masses to left-handed neutrinos through mixing. The heavier the right-handed neutrinos, the lighter the left-handed ones, like a seesaw. Masses of 10 to 15 GeV for right-handed neutrinos give 0.1 electron volts for left-handed ones. But we've never detected right-handed neutrinos. They'd be so heavy that producing them in accelerators is impossible. They're hypothetical, invoked to explain the data, but unobserved. Neutrinos are the least understood particles in the standard model. We know they exist, we've detected them, we've measured some of their properties. But fundamental questions remain. Let's talk about the Casimir effect more deeply. 2 uncharged metal plates in vacuum attract each other. This seems impossible. There's no matter between them, no classical force. But quantum mechanics predicts it, and experiments confirm it. The vacuum between the plates excludes certain wavelengths of virtual photons, those too large to fit. Outside the plates, all wavelengths exist. This creates a pressure difference, pushing the plates together. The vacuum has structure, and that structure exerts force. The Casimir effect is tiny, measurable only for plates micrometers apart. But it's real, and it has technological implications. In microelectromechanical systems, MEMS, Casimir forces can affect operation, causing stiction, where surfaces stick together. But the Casimir effect also raises questions. What is the vacuum? Is it really a thing with energy and structure? Or is it a mathematical convenience, a way of organizing calculations? Different approaches to quantum field theory give different answers. In the standard approach, the vacuum is the lowest energy state of the quantum fields, but it's not empty. It's filled with zero-point energy fluctuations that arise from the uncertainty principle. In other approaches, the vacuum is truly empty, and Casimir forces arise from correlations between the plates, not from vacuum energy. These give the same predictions, so experimentally you can't distinguish them. But conceptually, They're very different. And which one is right if either is unclear? Here's something from astrophysics: the cooling problem in galaxy clusters. X-ray observations of galaxy clusters show hot gas, millions of degrees, filling the space between galaxies. This gas should cool, radiating away its energy, condensing into stars. But it doesn't. The cooling rate is much slower than expected. Something is heating the gas, counteracting the cooling. The leading candidate is feedback from the central supermassive black hole. Jets from the black hole inject energy into the gas, stirring it, heating it, preventing cooling. But the feedback has to be finely tuned. Too much heating and the gas blows away. Too little and it cools and collapses. Yet galaxy clusters maintain a balance, persisting for billions of years. How? This is called the cooling flow problem, and it's related to galaxy formation in general. If gas cooled efficiently, we'd have far more stars than we observe. Something regulates star formation, keeping it inefficient, wasteful. Supernovae, stellar winds, black hole feedback, they all contribute. But the details are complex, poorly understood. We're simulating galaxy formation on supercomputers, including feedback, trying to reproduce observations. Progress is being made, but challenges remain. Simulations are expensive, and the physics is multiscale, spanning parsecs to megaparsecs, microseconds to billions of years. Let me tell you about the fate of the universe in more detail. If dark energy is constant, a cosmological constant, then the universe will expand forever, accelerating. Galaxies will disappear beyond the cosmic horizon, one by one. In 1 trillion years, the night sky will be dark, empty, except for the local group of galaxies bound by gravity. Stars will exhaust their fuel, dying as white dwarfs, neutron stars, black holes. No new stars will form because gas will be too dispersed. The universe will darken, cooling toward absolute zero. After 10 to 100 years, protons might decay, turning matter into radiation. If they don't, matter will persist, but it'll be locked in dead stars, cold, dark, unreactive. After 10 to 100 years, black holes will be the only macroscopic objects left, slowly evaporating via Hawking radiation. The smallest black holes evaporate first. Supermassive ones last longer, but eventually they too disappear. After 10 to 100 years, maybe 10 to 150 years, the universe will be truly dead. Only photons, neutrinos, maybe gravitons spreading thinner and thinner, cooling towards zero energy. Heat death, the ultimate fate, the final state of maximum entropy. Unless dark energy changes. If it increases, the expansion could accelerate to infinity in finite time. A big rip, tearing apart galaxies, stars, planets, atoms, nuclei, quarks. Everything shredded by expanding space. Or if dark energy decreases or reverses, gravity could regain control. The expansion could halt and reverse, leading to a big crunch, the opposite of the Big Bang. The universe collapses, heating up, compressing, ending in a singularity. Or maybe cycles. Crunch followed by bounce, bounce by expansion, expansion by crunch, eternally repeating. Or maybe collision with another universe, a brain collision in higher dimensions, restarting everything. We don't know. The far future depends on dark energy, and we don't understand dark energy. We're extrapolating billions and trillions of years based on measurements made over decades. It's audacious, possibly foolish, but it's the best we can do. And it matters. The fate of the universe is the fate of everything. Life, consciousness, meaning. If the universe dies in heat death, is everything ultimately futile? Or is the journey enough? regardless of the destination? These are questions that science touches but can't fully answer. They require philosophy, values, choices about what matters. Science tells us what is and what will be. But whether that's okay, whether it's good or bad, that's beyond science. Now let me tell you about something remarkable: the cosmic microwave background cold spot. It's a region about 10 degrees across, where the temperature is about 70 microkelvins colder than average. It was first detected by WMAP and confirmed by Planck. Is it a statistical fluke? Simulations say there's about a 1% chance of such a large cold spot appearing randomly. That's low but not impossible. Maybe we got unlucky, or maybe it's real, pointing to something unexpected. One possibility: a supervoid, an unusually empty region of space along the line of sight. Photons climbing out of the void lose energy, creating a cold spot. But the void would have to be enormous, larger than predicted by standard structure formation models. Another possibility: a topological defect, a cosmic texture, or other relic from the early universe. These could create cold spots, but they're exotic, not predicted by the simplest models. Or maybe a collision with another universe. If we're in a multiverse, and another universe bumped into ours early in cosmic history, it could leave a bruise, an anomaly in the CMB. This sounds like science fiction, but some multiverse models predict observable signatures. The cold spot sits there, in the southern sky, unexplained, statistically anomalous, possibly meaningless, possibly profound. We won't know until we understand it better, map the surrounding structure, rule out or confirm the various hypotheses. Let's discuss the maximum temperature. The Planck temperature, about 10 to 32 Kelvin. Above this temperature, quantum gravity effects become important, and our theories break down. We can't describe physics at higher temperatures because we don't have a theory of quantum gravity. The Planck temperature was reached about 10 to 43 seconds after the Big Bang, during the Planck epoch. Before that, we can't say what happened. Space and time might not have existed as we understand them. The concepts might be meaningless. Some models propose that the Big Bang wasn't the beginning. The universe bounced from a previous contracting phase, or it emerged from a quantum fluctuation in a pre-existing space, or it's one phase in an eternal multiverse. But these are speculations. We have no observational access to the Planck epoch. The earliest we can probe is around 10 to 32 seconds, the end of inflation, when the universe was still incredibly hot but below the Planck temperature. The Planck scale sets limits on what we can know. Not technological limits, but fundamental ones, imposed by the structure of spacetime and quantum mechanics. Some questions might be permanently beyond our reach, not because we're not clever enough, but because reality forbids asking them. Here's a final mystery, one that ties together many threads: the arrow of time at the microscopic level. I've talked about entropy and the macroscopic arrow, but there's also a microscopic arrow visible in weak interactions. The weak force violates time reversal symmetry, or more precisely, violates the combination of charge conjugation, parity, and time reversal, CPT. Certain decays happen at different rates forward and backward in time. This is called T violation, and it's been observed in kaons and B mesons. T violation is tiny, a fraction of a % effect. But it's real, and it's not explained by thermodynamics or entropy. It's built into the fundamental interactions. The weak force has a preferred direction in time. This might be connected to the baryon asymmetry. If processes violate T symmetry, they can create more matter than antimatter, explaining why we exist. But the amount of T violation we've observed isn't enough. There must be more from unknown sources, probably at higher energies. T violation is also connected to CP violation through the CPT theorem, which states that combined CPT must be a symmetry of any relativistic quantum field theory. If T is violated, so is CP. And we've observed CP violation too in the same systems. The patterns are tantalizing but incomplete. We're seeing hints of something deeper, a structure to the fundamental forces that goes beyond the standard model. But we haven't pieced it together yet. So where does this leave us? We've explored dozens of paradoxes, from the Fermi paradox to the information paradox, from dark matter to dark energy, from quantum measurement to cosmic expansion. Each one is a window into the unknown, a place where our understanding falters. But here's the thing. These paradoxes aren't signs of failure. They're signs of progress. We know enough to identify the problems, to articulate the questions, to recognize where our theories break down. That's enormous progress compared to a century ago, when we didn't even know these questions existed. And progress continues. Every year, new observations, new experiments, new theoretical insights. The boundaries of knowledge expand. The paradoxes evolve, some resolved, new ones emerging. It's a dynamic process, a conversation between theory and experiment, between ideas and reality. We're privileged to live in this era, the era when we can see the cosmic microwave background, detect gravitational waves, discover exoplanets, peer into black holes. The era when we can ask fundamental questions about the nature of reality and have tools powerful enough to make progress. Our descendants, centuries or millennia from now, will look back at our time as a golden age of discovery. Not because we solved everything, but because we opened up the cosmos, revealed its strangeness, laid the foundations for future understanding. And they'll have their own paradoxes, their own mysteries, born from what we discover today. The frontier never stops. Every answered question spawns new ones. That's not a bug, it's a feature. It's how science works, how knowledge grows, how we transcend our limitations. So embrace the paradoxes. Let them inspire you, challenge you, keep you awake at night, because they're invitations to participate in something larger than yourself, to contribute to humanity's collective understanding, to be part of the cosmic story. The universe is strange, beautiful, terrifying, magnificent, and it's waiting for you to explore it. This is SOSM Hush, reminding you one last time. Keep looking up, keep asking why, and never stop wondering. Because the cosmos has secrets, and together we're going to uncover them. The paradoxes that keep scientists awake at night are the paradoxes that should inspire us all. They're proof that reality is richer than we imagined, that there's always more to discover, that the adventure never ends. So go forth, ask questions, challenge assumptions, push boundaries, make discoveries. The universe is calling. Will you answer? I already know you will, because you're here listening, learning, wondering, and that's all it takes. The cosmos is vast. The mysteries are infinite, and you're part of the solution. Welcome to the frontier. Welcome to the adventure. Welcome to the rest of your life. SOSM Hush, signing off. Until next time, keep your eyes on the stars and your mind on the impossible. Because in the cosmos, the impossible happens every day, and the greatest discoveries are yet to come. This is SOSM Hush, reminding you that reality is stranger than you think. And that's exactly why it's worth exploring. But we're not done yet. There's more to unpack, more paradoxes lurking in the shadows of our understanding. Let me tell you about something that connects quantum mechanics to the very fabric of reality. the Heisenberg uncertainty principle. You can't simultaneously know a particle's exact position and momentum. The more precisely you measure one, the less precisely you can know the other. This isn't about measurement error or clumsy instruments. It's fundamental, built into the structure of reality itself. But here's what most people miss. The uncertainty principle isn't just about particles. It applies to energy and time too. The shorter the time interval, the greater the uncertainty in energy. This has profound consequences. It means that over very short timescales, energy conservation can be violated. The universe can borrow energy from nowhere as long as it pays it back quickly enough. This is how virtual particles work. Particle-antiparticle pairs pop into existence, exist for a fleeting moment, and annihilate. They violate energy conservation, but only briefly, within the limits allowed by the uncertainty principle. The vacuum is seething with these quantum fluctuations, a bubbling foam of particles appearing and disappearing, too fast to catch directly. And these virtual particles have real effects. The Casimir effect, where two metal plates experience an attractive force in vacuum, is caused by virtual particles. The plates exclude certain wavelengths of virtual particles, creating an imbalance, a pressure difference that pushes them together. Empty space pushes on matter. The Lamb shift in hydrogen atoms, a tiny difference in energy levels that shouldn't exist classically, is caused by the electron interacting with virtual photons. The electron's interaction with the seething vacuum slightly changes its energy, and we can measure this change with extraordinary precision. Even mass is affected. Most of a proton's mass doesn't come from its constituent quarks. It comes from the energy of the gluon field binding them together, from the kinetic energy of quarks zipping around at near light speed, from virtual quark-antiquark pairs popping in and out of existence. The proton is a maelstrom of quantum activity, and mass emerges from that activity. This should trouble you. Mass, the thing that seems most solid, most real, is actually energy in disguise, arising from quantum processes we can barely visualize. You're not made of stuff. You're made of patterns, of fields oscillating, of energy organized into temporary structures we call atoms, molecules, cells. And here's another layer of weirdness. Quantum field theory, our best description of particles and forces, is an approximation. It assumes space-time is flat, unchanging, a backdrop on which quantum fields perform. But general relativity says space-time is dynamic, curved by mass and energy. These two frameworks don't play well together. When you try to do quantum field theory on curved spacetime, strange things happen. The definition of a particle becomes observer-dependent. What's a particle for one observer is not a particle for another. The vacuum isn't universal. It depends on your reference frame, your motion, your position in a gravitational field. This is called the Unruh effect for acceleration and Hawking radiation for black holes. They're different manifestations of the same phenomenon. Quantum fields behave differently in different coordinate systems. And if particles aren't universal, if their existence depends on perspective, then what's real? Maybe fields are real, and particles are convenient fictions. Maybe spacetime is real, and fields are convenient fictions. Maybe both are emergent from something deeper, something we haven't discovered yet. Let's talk about neutron stars more deeply. They're strange beyond imagining. A neutron star is about 20 kilometers in diameter but contains more mass than the Sun. Its surface gravity is 200 billion times stronger than Earth's. If you dropped an object from 1 meter above the surface, it would hit the ground at millions of meters per second. The impact would release more energy than a nuclear bomb. The density is staggering. A teaspoon of neutron star matter weighs about 1 billion tons. It's compressed to nuclear density, the density at which atomic nuclei touch, squeezing out all the empty space. Electrons and protons can't maintain their separate identities under such pressure. They merge, forming neutrons. The entire star becomes a gigantic atomic nucleus, held together by gravity. But neutron stars aren't uniform. They have layers. The surface is a solid crust of iron nuclei arranged in a crystalline lattice, the strongest material in the universe. Below that, nuclei become more exotic, deformed into rods and slabs and weird geometries called nuclear pasta. Deeper still, nuclei dissolve entirely, and you enter a superfluid of neutrons, flowing without viscosity, conducting heat perfectly. At the very core, we're not sure what exists. The pressure might be so high that neutrons break down into quarks, forming a quark-gluon plasma, a state of matter that existed microseconds after the Big Bang and nowhere else since. Or maybe there are hyperons, particles containing strange quarks. Or maybe pion condensates or kaon condensates, or phases of matter we haven't imagined. We can't probe the interior of neutron stars directly, but we can observe their behavior and infer what's inside. The maximum mass of a neutron star depends on the equation of state, the relationship between pressure and density. If the core is soft, easily compressed, neutron stars can't be very massive. If it's stiff, resistant to compression, they can be heavier. Recent observations of massive neutron stars, around 2 solar masses, and mergers detected by gravitational waves, constrain the equation of state. The core is stiffer than we thought, but not as stiff as some models predicted. We're narrowing in on the truth one observation at a time. And neutron stars have magnetic fields that defy comprehension. Magnetars have fields around 10 to 15 Gauss, strong enough to rip atoms apart, to make space itself birefringent, splitting light into different polarizations. If you were within 1,000 kilometers of a magnetar, your body's molecular bonds would be disrupted. Your atoms would be stretched into cigars. You die in ways medicine doesn't have names for. These fields decay over time, releasing energy as X-rays and gamma rays. Sometimes they release too much energy too fast, producing giant flares, eruptions that briefly rival supernovae. The energy comes from the magnetic field itself, from the field lines twisting and reconnecting, releasing stored energy in catastrophic bursts. And magnetars might be more common than we think. They fade after a few thousand years, becoming invisible, but they don't disappear. They're still out there, dark, silent, cooling. Some fraction of the galaxy's neutron stars might be extinct magnetars, remnants of a violent phase we can no longer observe. Here's a puzzle that touches on fundamental physics. The strong CP problem. The strong nuclear force which binds quarks into protons and neutrons should violate CP symmetry, the combination of charge conjugation and parity. The equations allow for CP violation, and there's no reason it shouldn't happen. But it doesn't. Experiments searching for CP violation in the strong force find nothing. The upper limit on the CP violating parameter is about 10 to minus 10, far smaller than you'd expect from natural values. Something is suppressing CP violation, forcing the parameter to be extraordinarily close to 0. But what? This is the strong CP problem, and it's one of the outstanding mysteries in particle physics. The most popular solution is the axion, a hypothetical particle predicted by the Pecchiai-Quinn mechanism. Axions would dynamically relax the CP violating parameter to 0, solving the problem naturally. Axions would be very light, millions of times lighter than electrons, and they'd interact incredibly weakly. They'd pass through ordinary matter as if it weren't there, but they'd interact with photons in strong magnetic fields, converting back and forth between axions and photons with a tiny probability. This makes axions detectable, at least in principle. You set up a cavity in a strong magnetic field, tune it to resonate with axion masses, and look for photons produced by axion conversions. Several experiments are doing exactly this. ADMX in the US cast at CERN IAXO. So far, nothing. But the parameter space is enormous, and we're searching methodically. If axions exist, they could be dark matter. They'd have been produced abundantly in the early universe, and they'd still be around, filling the galaxy, passing through you right now. Dark matter could be a side effect of solving the strong CP problem, two mysteries resolved by one particle. Or maybe axions don't exist. Maybe the strong CP problem is solved some other way, through new symmetries or anthropic selection or something we haven't thought of. Or maybe it's not a problem at all, and the CP violating parameter is naturally small for reasons we don't understand yet. Let me tell you about tidal disruption events, one of the most violent spectacles in the cosmos. When a star wanders too close to a supermassive black hole, the tidal forces, the difference in gravitational pull between the near side and far side of the star, tear it apart. The star is spaghettified, stretched into a thin stream of gas that wraps around the black hole and eventually falls in. As the gas falls, it heats up, reaching temperatures of millions of degrees, emitting X-rays and UV radiation. The flare lasts for months to years, gradually fading as the gas is consumed. We've detected dozens of tidal disruption events, each one a death scream from a star that ventured too close. But they're not all the same. Some produce relativistic jets, beams of particles traveling at near light speed. Others don't. Some flare in optical light, others in X-rays, others in radio waves. The diversity suggests that the details matter. The mass of the black hole, the type of star, the angle of approach, the spin of the black hole. And some tidal disruption events are weird. Some repeat, flaring multiple times, which shouldn't happen if the star is destroyed. Maybe it's a white dwarf that gets partially disrupted, survives, and orbits back for another encounter. Maybe it's a binary system where one star is disrupted and the other continues, eventually being disrupted itself. There's also the mystery of how often these events occur. Based on the rate we detect them and the volume of space we survey, tidal disruption events should happen once every 10,000 to 100,000 years per galaxy. That seems rare, but there are billions of galaxies, so we should be detecting many more than we do. Maybe we're missing most of them. Maybe they're obscured by dust, or they flare in wavelengths we're not monitoring, or they happen in galaxy cores where other activity masks them. Or maybe our models of stellar dynamics are wrong, and stars don't approach black holes as often as we think. Either way, tidal disruption events are laboratories for extreme physics. They probe the properties of black holes, test general relativity in strong fields, trace the distribution of stars in galaxy centers. And they're spectacular, cosmic disasters playing out on timescales we can watch in real time. Here's something that should make you uncomfortable. The black hole information loss problem isn't solved. I mentioned it earlier, but it's worth revisiting because it goes to the heart of quantum mechanics. When something falls into a black hole, information about it seems to be lost. But quantum mechanics says information can't be destroyed, can be scrambled, hidden, encrypted, but not lost. Stephen Hawking spent decades on this problem. In 1974, he showed black holes radiate, slowly evaporating, and he argued that the radiation is thermal, carrying no information about what fell in. Information is lost, violating quantum mechanics. He called this the information paradox. For years, physicists debated. Some argued information is preserved, encoded somehow in the radiation or on the horizon. Others argued quantum mechanics needs modification. Hawking himself changed his mind multiple times. In 2004, Hawking conceded that information is preserved, though he didn't explain how. The firewall paradox in 2012 reignited the debate, showing that preserving information leads to contradictions. We're back to square one, decades later, still arguing about the same problem. Recent work suggests the answer involves quantum entanglement and the holographic principle. Information isn't lost because it was never really inside the black hole. It's encoded on the horizon holographically, and the interior is a kind of projection, an emergent space constructed from entanglement on the boundary. This is wild. It means black holes aren't what we thought they were. They're not bags of matter hidden behind horizons. They're information processing systems, quantum computers of a sort, with all the data stored on the surface. The interior is a useful fiction, a way of describing correlations in the boundary degrees of freedom. But this raises new questions. If the interior is emergent, what happens when you fall through the horizon? Do you experience a smooth passage as general relativity predicts? Or do you hit a firewall, a wall of high-energy particles that incinerates you? Different approaches to the information paradox give different answers. We won't resolve this without quantum gravity. We need a theory that unifies quantum mechanics and general relativity, that describes black holes from first principles. String theory and loop quantum gravity offer possibilities, but neither is complete. We're still searching for the right framework, and the stakes are high. If we're wrong about black holes, we might be wrong about space-time, about quantum mechanics, about the very foundations of physics. The information paradox is a crack in the edifice, and it might bring down the whole structure. Let's talk about cosmic rays, high-energy particles that rain down on Earth from space. Most are protons, some are heavier nuclei, a few are electrons. They're accelerated somewhere in the cosmos by supernovae or pulsars or active galactic nuclei, and they travel through space for millions of years before hitting Earth. We've studied cosmic rays for over a century, but mysteries remain. We don't know exactly where they come from. We don't know how they're accelerated to such high energies. The highest energy cosmic rays have energies above 10 to 20 electron volts, equivalent to a baseball traveling at 60 miles per hour, concentrated in a single proton. What can do that? The leading model is diffusive shock acceleration. Particles bounce back and forth across a shock front, like a wave breaking, gaining energy with each crossing. Supernova shocks, the expanding shells of debris from exploding stars, are prime candidates. They're fast, strong, and ubiquitous. But supernova shocks might not be enough for the highest energies. You need something more powerful. Maybe gamma-ray bursts, the most energetic explosions in the universe. Maybe active galactic nuclei, the jets from supermassive black holes. Maybe exotic sources we haven't identified yet. And cosmic rays interact with the cosmic microwave background. Above a certain energy, around 5x10 to 19 electron volts, protons collide with CMB photons, producing pions, losing energy rapidly. This is the GZK cutoff, and it means ultra-high energy cosmic rays can't travel far, only about 50 megaparsecs. So the sources must be nearby. But we don't see obvious sources. No gamma-ray bursts, no active galactic nuclei in the right locations. The cosmic rays seem to come from random directions, pointing nowhere in particular. Maybe they're deflected by magnetic fields. Galactic and extragalactic magnetic fields can bend cosmic ray trajectories, scrambling their directions. But even accounting for this, the sources are elusive. Or maybe the cosmic rays aren't protons. Maybe they're heavier nuclei, iron or silicon, which interact differently with the CMB and can travel farther. Or maybe they're not accelerated astrophysically at all. Maybe they're decay products of supermassive particles from the early universe, relics of new physics at ultra-high energies. We don't know. And every ultra-high energy cosmic ray we detect is a puzzle, a messenger from the cosmos that we can't quite decode. Here's a philosophical question with physical implications. What is a law of nature? We talk about the laws of physics, equations that govern how the universe works. But what makes them laws? Why does the universe obey them? Why these laws and not others? You might say the laws are just descriptions, patterns we've noticed. The universe doesn't obey the laws. The laws describe what the universe does. But that seems unsatisfying. The laws are extraordinarily precise, universal, unchanging. They hold everywhere in the observable universe at all times. That's remarkable. It demands explanation. Maybe the laws are necessary consequences of logical or mathematical truths that couldn't be otherwise. But mathematics is full of arbitrary choices, axioms we assume because they're useful, not because they're inevitable. And different mathematical systems lead to different physics. Why this particular set of axioms? Maybe the laws evolved, somehow selected from many possibilities. Maybe there's a multiverse and different universes have different laws, and we exist in one where the laws permit complexity, structure, life. This is the anthropic principle again, and it's controversial. Or maybe the laws are emergent, not fundamental. Maybe at the deepest level, there are no laws, just quantum randomness or chaos. The laws we see are statistical regularities, averages over microscopic disorder, like how thermodynamics emerges from molecular motion. This is speculative, but some approaches to quantum gravity suggest something like this. Space and time are emergent, not fundamental. If space and time are emergent, maybe the laws are too, arising from deeper processes that don't follow laws at all. But this is uncomfortable. We're scientists. We believe in order, in cause and effect, in predictability. The idea that the laws are accidents or emergent or contingent undermines everything. Yet we have to consider it because the alternative, that the laws are necessary, doesn't seem to work either. So we're left with a mystery. The laws exist, they work, we can use them to predict and explain. But we don't know why they exist, why they work, why they're the laws they are. It's a meta-question hovering above physics, touching philosophy and theology and mathematics. And maybe that's okay. Maybe some questions don't have answers within science. Maybe the existence of laws is a boundary condition, something we have to accept to do science at all. But acknowledging that doesn't make the question go away. Let me tell you about Hawking radiation in more detail because it's one of the most beautiful ideas in theoretical physics. Black holes emit radiation, not because something escapes from inside the event horizon, but because quantum effects near the horizon create particle-antiparticle pairs. One falls in, the other escapes. To an external observer, the black hole is radiating. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass black holes are cold, around 10 to minus 7 Kelvin, far colder than the cosmic microwave background. They absorb more radiation than they emit, growing slowly. But smaller black holes are hotter. A black hole with the mass of a mountain would be hot enough to glow, emitting visible light, X-rays, gamma rays. And as a black hole radiates, it loses mass. The process accelerates. As it gets smaller, it gets hotter, radiating faster, losing mass faster. Eventually, It explodes, releasing its remaining mass as radiation in a final burst. A mountain mass black hole would evaporate in about a second, releasing energy equivalent to millions of nuclear bombs. This is called Hawking radiation, and it's never been observed. The effect is too small for astronomical black holes, but it's theoretically solid, arising from quantum field theory in curved spacetime. If Hawking was right, and most physicists think he was, then black holes aren't eternal. They evaporate. Given enough time, all black holes will disappear. This has profound implications for the fate of the universe. In the far future, after stars have died, after galaxies have dispersed, after protons have decayed, black holes will be the last macroscopic objects, slowly evaporating, the final sources of energy in a cold, dark universe. And when the last black hole evaporates, the universe will be truly dead, a thin soup of photons and neutrinos, expanding forever, cooling toward absolute zero. But Hawking radiation creates the information paradox. If a black hole evaporates completely, where does the information go? The radiation is thermal, random, carrying no information about what formed the black hole or what fell into it. Information seems to be destroyed, violating quantum mechanics. Some propose that information leaks out slowly, encoded in subtle correlations in the Hawking radiation. Others propose that a remnant remains after evaporation, a tiny object containing all the information. Others propose modifications to Hawking's calculation, suggesting the radiation isn't purely thermal but contains information. None of these solutions is fully satisfying. We're missing something, some insight that will make it all click. And until we have it, the information paradox remains a thorn in the side of theoretical physics. Here's something that doesn't get enough attention: the cosmic optical background. We've measured the cosmic microwave background, the infrared background, the X-ray background. But the optical background, the sum of all starlight integrated over cosmic history, is harder to measure because the sky is bright. Our sun, zodiacal light, air glow, they all contaminate the signal. But we've made progress using spacecraft, observing from locations away from Earth, where the sky is darker. And what we find is puzzling. The optical background is brighter than expected. There's more light than can be accounted for by known galaxies and stars. Where's the extra light coming from? Maybe there are more galaxies than we thought, faint dwarfs we've missed. Maybe intracluster stars, stars between galaxies in clusters, contribute. Maybe there's a population of rogue stars, ejected from galaxies, floating in intergalactic space. Or maybe the light is from the first stars, population 3 stars, massive, short-lived, formed from primordial gas before metals existed. We've never seen a population 3 star directly. They should have died billions of years ago, leaving no remnants. But their light would still be traveling through space, contributing to the cosmic background. The cosmic optical background is a probe of the universe's history, a way of counting every photon ever emitted. And if the background is brighter than expected, it's telling us something about cosmic history we don't fully understand yet. Let's discuss entropy and the arrow of time more carefully. The second law of thermodynamics says entropy increases in isolated systems. Hot coffee cools, ice melts, gases mix. Order becomes disorder. This gives time a direction, an arrow pointing from past to future. But the fundamental laws of physics are time-symmetric. Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations, they all work the same forward and backward in time. If you film a single particle moving and play it backward, you can't tell. The physics is identical. So where does the arrow of time come from? Why does entropy increase? The answer involves initial conditions. The Big Bang started with low entropy, a highly ordered state. Since then, entropy has been increasing, and it will continue to increase until the universe reaches maximum entropy, a state of heat death where nothing happens, nothing changes, nothing can happen. But this just pushes the question back. Why was entropy low at the Big Bang? Why did the universe start in an ordered state? If the initial conditions were random, you'd expect maximum entropy, not minimum. The fact that the universe started with low entropy is profoundly improbable, requiring explanation. Some invoke inflation. Inflation produces a low entropy state naturally, stretching away inhomogeneities. But inflation itself requires special initial conditions, so you haven't really solved the problem. Others invoke cosmological selection, arguing that only low-entropy universes can support observers, so of course we find ourselves in one. This is unsatisfying because it doesn't explain why the universe exists, only why we see what we see. Maybe entropy is subjective, dependent on what information you have. If you knew the exact microstate of the universe, entropy would be zero by definition. But you don't, so you assign probabilities, and those probabilities correspond to entropy. The arrow of time is epistemic, not ontological, a feature of our knowledge, not of reality. This is controversial. It implies that the arrow of time is observer-dependent, that different observers with different information could disagree about which direction is the future. But our experience of time is robust, objective, shared. We all age, we all remember the past, but not the future. Can this really be subjective? The arrow of time remains one of the deepest problems in physics, connecting thermodynamics, cosmology, quantum mechanics, and philosophy. And we're no closer to solving it now than we were a century ago. Let me end with one more thought. Throughout this journey, we've encountered paradoxes, mysteries, questions without answers. And you might feel frustrated, unsettled, maybe even a little hopeless. We don't know so much. The universe is so strange. How can we ever understand it? But here's the thing. The fact that we can ask these questions is extraordinary. The fact that we've discovered paradoxes means we've probed deep enough to find the limits of our current understanding. That's progress. That's success. A century ago, we didn't know about the expanding universe, about quantum mechanics, about black holes. We've learned so much so fast. And yes, every answer raises new questions, but that's not a bug. It's a feature. It means reality is richer than we imagined, more complex, more interesting. The paradoxes aren't walls. They're doors. They're invitations to think deeper, to question assumptions, to explore new possibilities. Every paradox solved reveals new layers of reality, new physics, new mathematics, new ways of seeing the cosmos. And the search is what matters. Not the destination, the journey, the process of inquiry, the struggle to understand, the collaboration, the creativity, the moments of insight, the breakthroughs and the dead ends, and the slow accumulation of knowledge. That's the essence of science. We're part of something larger than ourselves, a collective endeavor spanning generations, cultures, continents. We stand on the shoulders of giants, building on work done by people we'll never meet, contributing to a body of knowledge that will outlast us. And that's beautiful. That's meaningful. That's enough. So when you look up at the night sky, when you contemplate these paradoxes, when you feel small and insignificant in the face of cosmic vastness, remember, you're the universe looking at itself. You're made of atoms forged in stars, arranged into patterns capable of wonder, of curiosity, of understanding. And that's a miracle. Not a supernatural miracle, but a natural one. A miracle of complexity emerging from simplicity, of consciousness arising from unconscious matter, of meaning creating itself in a cosmos that started without it. The paradoxes will keep us awake. The mysteries will haunt us. The questions will multiply faster than the answers. But that's okay, because the alternative, a universe without mystery, without paradox, without questions, would be a universe not worth living in. So embrace the paradoxes, chase the mysteries, ask the questions that have no answers yet, because that's what it means to be human. That's what it means to be part of this cosmic story. The universe is strange. Reality is weird. And that's exactly why it's worth exploring. This is COSM Hush. Keep wondering, keep questioning, and never stop looking up. The cosmos has secrets, and we're going to find them. But before we part ways, let me leave you with a few more paradoxes, some final mysteries to ponder as you drift off to sleep tonight. Consider the paradox of scale. The universe operates on scales so extreme that they break our intuition. At the quantum scale, things exist in multiple states simultaneously. At the cosmic scale, space itself is expanding, carrying galaxies away from each other faster than light. And between these extremes, in the comfortable middle ground where we live, the laws seem different, more familiar. Why? Why does the universe have this layered structure where different physics applies at different scales? It's called the hierarchy problem, and it plagues particle physics. The Higgs boson, which gives mass to particles, has a mass around 125 GeV. But quantum corrections should push its mass up to the Planck scale, 10 to 19 GeV. Something is canceling these corrections with incredible precision, keeping the Higgs mass low. Supersymmetry was supposed to solve this, predicting partner particles that cancel the corrections naturally. But we've searched for supersymmetric particles at the Large Hadron Collider and found nothing. Either supersymmetry is broken at higher energies than we can probe, or it doesn't exist, or nature uses a different mechanism we haven't thought of. The hierarchy problem touches on anthropic questions too. If the Higgs mass were much higher, atoms would be unstable, chemistry wouldn't work, life couldn't exist. We're here because the Higgs mass has the value it does. But why does it have that value? Is it selected from a landscape of possibilities? Is it fine-tuned by design? Is there a deeper principle that fixes it uniquely? We don't know. And the hierarchy problem sits there, unresolved, a reminder that even our most successful theory, the Standard Model, is incomplete. Here's another one, the cosmological coincidence problem. Dark energy and matter have comparable densities right now, in the present era. But they evolve differently. Matter dilutes as the universe expands, its density dropping. Dark energy stays constant, its density unchanging. In the past, matter dominated. In the future, dark energy will dominate. We happen to live in the brief cosmic moment when they're comparable. Why? Is it a coincidence? Or is there a connection between dark energy and matter that we don't understand? Some theories propose that dark energy is dynamical, tracking the matter density, staying comparable. Others propose anthropic selection. Observers can only arise when the densities are comparable because structure formation requires it. Neither explanation is satisfying. The coincidence problem remains, nagging at cosmologists, suggesting there's something about dark energy we're missing. And let me tell you about the vacuum catastrophe, one of the worst predictions in the history of physics. Quantum field theory predicts that empty space has energy arising from zero-point fluctuations of quantum fields. We can calculate this energy density, and the answer is catastrophic. 10 to 113 joules per cubic meter. Compare that to observations. Dark energy has a density of about 10 to minus 9 joules per cubic meter. The prediction is off by 122 orders of magnitude. That's not a small error. That's a colossal failure. Something must cancel the quantum vacuum energy, suppressing it to nearly zero but not quite. What's doing the canceling? We have no idea. Supersymmetry was supposed to help, with bosons and fermions contributing opposite signs. But even with supersymmetry, the cancellation isn't perfect. You still need fine-tuning. Some invoke anthropic reasoning. In a multiverse with different vacuum energies, only universes with small vacuum energy can form galaxies, stars, planets, life. We're in one such universe not because it's typical but because it's habitable. But this doesn't explain the mechanism, only why we observe what we observe. The vacuum catastrophe is an embarrassment. It suggests we're missing something fundamental about quantum field theory or gravity or both. And until we solve it, we can't claim to understand the vacuum, the very foundation on which everything rests. Let's talk about the Pauli exclusion principle, which states that no two fermions can occupy the same quantum state. Electrons, protons, neutrons, they're all fermions, and they obey the exclusion principle. This is why matter is solid, why atoms have structure, why chemistry works. Without the exclusion principle, all electrons would collapse into the lowest energy state, and matter would have radically different properties. But why do fermions obey the exclusion principle? It's a consequence of their quantum statistics related to how their wave functions behave under particle exchange. Fermion wave functions are antisymmetric. Swap two fermions, and the wave function changes sign. This antisymmetry automatically enforces the exclusion principle. But why are some particles fermions and others bosons? It's related to spin and intrinsic angular momentum. Particles with half-integer spin are fermions. Particles with integer spin are bosons. But this connection, the spin statistics theorem, is deep and subtle. It's a consequence of relativistic quantum field theory, of how causality and quantum mechanics interact. And spin itself is weird. It's not rotation in the classical sense. Electrons don't spin like tops. Spin is an intrinsic property, like mass or charge, with no classical analog. When we say an electron has spin 1/2, we mean it behaves in certain ways under rotations, transforming according to specific mathematical rules. Some particles have no spin at all, like the Higgs boson. Some have spin 1, like photons. Some have spin 2, like gravitons, the hypothetical particles of gravity. The hierarchy of spins corresponds to a hierarchy of forces and interactions, all emerging from the symmetries of spacetime and quantum mechanics. It's beautiful, elegant, mathematically sophisticated, but it's also abstract, far removed from everyday experience. We're describing reality in a language that has no direct connection to what we see and feel. And that disconnect is both the power and the limitation of modern physics. Here's a cosmological mystery: the dipole anomaly in the cosmic microwave background. The CMB isn't perfectly uniform. It has a dipole pattern warmer in one direction, cooler in the opposite direction, by about 0.1%. This is caused by our motion through space. We're moving at about 370 kilometers per second relative to the CMB rest frame, toward a point in the constellation Leo. But here's the anomaly. When we measure the dipole using different tracers, radio galaxies, quasars, X-ray sources, we get slightly different answers. The dipoles don't quite line up. The amplitudes differ. The subtle, barely significant statistically, but it's there. What's causing it? Maybe our motion is more complicated than we thought, with local flows superimposed on the cosmological velocity. Maybe there's structure in the universe on scales larger than we've accounted for, affecting different tracers differently. Maybe it's a systematic error, a bias in how we select sources or measure distances. Or maybe it's telling us something deeper. Maybe the universe isn't perfectly isotropic. Maybe there are preferred directions, violations of the cosmological principle. Maybe we're seeing evidence of a multiverse, where our universe is embedded in a larger structure with its own anisotropies. It's probably nothing. Most anomalies in cosmology turn out to be measurement issues or statistical flukes, but some don't. And the dipole anomaly is one to watch because if it's real, it's revolutionary. Let me tell you about the maximum entropy of a region, the Bekenstein bound. It states that the entropy of a region with radius r and energy E cannot exceed 2 r/c, where is the reduced Planck constant and c is the speed of light. This is a fundamental limit imposed by the fact that if you exceed it, the region collapses into a black hole, and black holes have the maximum entropy possible for a given size. The Bekenstein bound has profound implications. It means there's a maximum amount of information that can be stored in a region. You can't pack arbitrarily much data into a finite volume. The universe has built-in limits on information density. This connects to the holographic principle. If the maximum entropy scales with area, not volume, then the information content of a region is determined by its surface, not its interior. The bulk is redundant, derivable from the boundary. The universe is a hologram, and this constrains computation. The ultimate laptop, the most powerful computer that can fit in a given volume, is limited by the Bekenstein bound. You can't process information faster than a certain rate without collapsing into a black hole. The universe has a maximum clock speed. These limits aren't technological. They're fundamental, imposed by the laws of physics. We can approach them, design systems that operate near the bounds, but we can't exceed them. The universe says no, and there's no way around it. This should humble us. We like to think that with enough time, enough resources, enough ingenuity, we can solve any problem, know anything, compute anything. But the universe has limits. Some things are unknowable, not because we're not smart enough, but because reality itself forbids knowing them. Here's one more mystery, one that connects to biology and chemistry: homochirality. Amino acids, the building blocks of proteins, come in two forms, left-handed and right-handed, mirror images of each other. But life uses only left-handed amino acids. Similarly, sugars in DNA are right-handed. Life is chiral, asymmetric, preferring one hand over the other. Why? In chemistry labs, when you synthesize amino acids, you get equal amounts of both hands, a racemic mixture. Nature doesn't prefer one over the other, yet life does. How did this asymmetry arise? Maybe it was chance. The first self-replicating molecule happened to be left-handed, and that became locked in, propagating through all subsequent life. Once the choice was made, there was no going back. This is the frozen accident hypothesis. Or maybe it was physics. The weak nuclear force violates parity, preferring left-handed particles. This creates a tiny energy difference between left and right-handed molecules, favoring one over the other. Over time, this tiny bias amplified, driving the selection of left-handed amino acids. Or maybe it came from space. Meteorites contain amino acids, and some show a slight excess of left-handed forms. Maybe the asymmetry was delivered from interstellar space, where circularly polarized light from neutron stars or other sources could have preferentially destroyed one hand, leaving the other. We don't know. And it matters because if life elsewhere in the universe uses right-handed amino acids instead of left-handed, their biochemistry would be fundamentally incompatible with ours. We couldn't eat their food. They couldn't eat ours. Our enzymes wouldn't recognize their molecules. It would be like matter and antimatter, incompatible at the deepest level. Homochirality is a puzzle at the intersection of physics, chemistry, and biology, a reminder that even the origin of life, something so fundamental to our existence, contains deep mysteries. And finally, let me tell you about the simulation hypothesis one more time, because it's worth pondering. Are we living in a simulation? Not in the science fiction sense, but in a rigorous computational sense. If consciousness can be simulated, if sufficiently advanced civilizations can create virtual realities indistinguishable from base reality, then simulated beings vastly outnumber real ones. Probabilistically, you're more likely to be simulated than real. This isn't idle speculation. Philosophers like Nick Bostrom have formalized the argument. Either civilizations never reach the capability to create simulations, or they choose not to, or we're almost certainly in a simulation. At least one of these must be true. Some dismiss this as unfalsifiable, and they're right. You can't prove you're not simulated any more than you can prove there's no invisible dragon in your garage. But the simulation hypothesis has testable consequences. If we're simulated, there might be glitches, errors, computational shortcuts. The universe might have a pixelated structure at the Planck scale. Certain processes might be simplified, approximated, less detailed than they should be. We've looked for these signs. We've found nothing definitive. The universe seems consistent, detailed, continuous down to the limits of our measurements. But absence of evidence isn't evidence of absence. A good simulation wouldn't have obvious flaws. And here's the disturbing part. If we're simulated, the simulators have control. They could pause the simulation, rewind it, alter it. They could delete us with a keystroke. Our reality is contingent on their whim. We're characters in a story, and the author can rewrite the plot. Some find this terrifying. Others find it oddly comforting. If we're simulated, maybe death isn't the end. Maybe consciousness persists in some higher reality, outside the simulation. Maybe the simulators are benevolent or at least indifferent, and we can go about our lives without worrying. The simulation hypothesis is a modern version of theological arguments, replacing God with a programmer, heaven with base reality. It's a way of grappling with existential questions using the language of computation and information theory. And whether it's true or not, it's worth thinking about because it forces us to question assumptions about reality, existence, consciousness. So there you have it. Dozens of paradoxes, mysteries, questions that keep scientists awake at night. Some might be solved in your lifetime. Others might take centuries. Some might never be solved. But that's the beauty of it. The universe is an endless source of wonder, of mystery, of questions that demand answers. And we're privileged to be here, now, in an age when we can ask these questions and have a reasonable hope of making progress. We're explorers on the frontier of knowledge, mapping terra incognita, charting the unknown. Every generation discovers something new, something that transforms our understanding. And the next generation will do the same, building on what we've learned, reaching further, seeing deeper. The cosmos is vast. The mysteries are infinite. And we're here, a species of curious apes, looking up at the stars and asking why. That's what it means to be human. That's what it means to be part of this cosmic story. And it's the greatest adventure there is. So keep asking questions. Keep challenging assumptions. Keep pushing the boundaries, because somewhere out there, in the darkness between the stars, in the quantum foam, in the mathematics and the physics and the data, are answers. And maybe, just maybe, you'll be the one to find them. The universe is waiting. The paradoxes are calling. And the greatest discoveries of all time haven't happened yet. This is COSM Hush. Thank you for joining me on this journey through the cosmic mysteries. Keep looking up, keep wondering, and never stop asking why. Because the cosmos has secrets, and together we're going to uncover them. Until next time, remember, you are the universe experiencing itself. You are stardust that learned to think. You are a pattern of atoms that woke up and started asking questions about its own existence. And that's not just poetic. That's literal truth. You are cosmically significant, not despite your smallness, but because of your ability to comprehend the vastness. You are the way the universe knows itself. So embrace that. Embrace the wonder, the mystery, the paradoxes. Embrace the discomfort of not knowing, the frustration of unanswered questions, the humility of standing before the infinite. Because that's where growth happens. That's where discovery happens. That's where we transcend our limitations and become something more. The paradoxes that keep scientists awake at night are the same ones that should inspire us all. They're invitations to think bigger, dream larger, reach further than we thought possible. Reality is stranger than fiction. The universe is more bizarre than the wildest science fiction. And we're just beginning to understand how deep the rabbit hole goes. So welcome to the frontier. Welcome to the edge of knowledge, where everything we know meets everything we don't. Welcome to the cosmic adventure. The journey continues, the questions multiply, and the universe keeps surprising us. Stay curious, stay humble, stay hungry for knowledge. The cosmos isn't just out there. It's in here too, in every atom of your body, in every thought in your mind, in the very act of asking these questions. You are the cosmos contemplating itself. And that's the most profound paradox of all. COSM Hush, signing off. Keep your eyes on the stars and your mind on the mysteries. The universe is calling. Will you answer? Hashtag cosmic paradoxes that keep scientists awake. Look up at the night sky. Go ahead, I'll wait. What you're seeing right now is a lie. Not because the stars aren't real, but because the light reaching your eyes left those distant suns hundreds, thousands, even millions of years ago. You're not seeing the universe as it is. You're seeing its ghost. And that's just the beginning of the cosmic mysteries that torment the greatest minds in science. I'm going to tell you about the paradoxes that keep cosmologists staring at their ceiling at 3 in the morning. The questions so profound, so fundamentally weird, that they shake the very foundation of what we think we know about reality. These aren't just academic puzzles. These are cracks in the fabric of our understanding, windows into something far stranger than we ever imagined. Let's start with something that should terrify you more than it probably does. The universe is vast.
Incomprehensibly vast.
There are more stars in the cosmos than grains of sand on all the beaches of Earth. More galaxies than you could count in 1,000 lifetimes. The numbers are so staggering that they lose meaning. We're talking about octillions of planets, countless worlds orbiting countless suns across billions of years of cosmic history. Now here's the thing that should make you uncomfortable. Where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who, during a casual lunch conversation in 1950, looked up and asked a question that still haunts us today. Where are they? If the universe is so vast, so old, so full of potential homes for life, then where are all the aliens? Where are the radio signals, the megastructures, the evidence of civilizations that should have had billions of years head start on us? Think about it. Our sun is relatively young, only 4.5 billion years old. There are stars out there that formed when the universe was just a cosmic infant. If life arose on planets around those stars, they've had billions of additional years to evolve, to develop technology, to spread across the galaxy. Even traveling at a fraction of light speed, a civilization could colonize the entire Milky Way in just a few million years. That's a cosmic blink. Yet we see nothing. We hear nothing. The galaxy is silent. The silence is deafening, and it points to something deeply troubling. Either we're alone, which is terrifying in its own right, or something prevents civilizations from making it to the point where they can spread among the stars. Some call it the Great Filter, a cosmic barrier that civilizations cannot pass. Maybe it's behind us. Maybe the jump from simple chemistry to self-replicating life is so improbable that we're the only ones who made it. Or maybe it's ahead of us. Maybe every civilization that reaches a certain level of technology inevitably destroys itself, and we're just waiting our turn. There's another possibility, even more unsettling. Maybe they're here and we just can't see them. Imagine ants trying to understand the internet. They crawl over fiber optic cables every day, completely oblivious to the torrents of information flowing beneath their feet. Maybe we're the ants, and advanced civilizations operate on levels we can't even perceive. They could be all around us, conducting business in dimensions we don't have access to, using physics we haven't discovered, thinking thoughts that would break our minds if we tried to comprehend them. Or perhaps the universe itself is the filter. Space is lethal. Radiation will kill you. Vacuum will kill you. The distances between stars are so vast that they might as well be infinite. Maybe intelligence is common, but interstellar travel is simply impossible, and every civilization is trapped on their homeworld, shouting into the void, wondering why no one answers. Now let me tell you about something that gets even stranger. Black holes. You know what they are, right? Regions of space-time where gravity is so intense that nothing, not even light, can escape. They're real, we've photographed them, we've detected their gravitational waves when they collide. But there's something about black holes that violates everything we know about how the universe works, and it's called the information paradox. Here's the deal. In physics, information cannot be destroyed. It's a fundamental law, as inviolable as the conservation of energy. If you burn a book, the information in that book isn't destroyed. It's scrambled, dispersed into heat and smoke and ash, but theoretically, if you could track every atom, every photon, you could reconstruct what the book said. The information is preserved. This principle underlies quantum mechanics, and if it's wrong, then reality itself is broken. But black holes present a problem. When something falls into a black hole, it disappears. Gone. According to general relativity, once matter crosses the event horizon, it's lost forever, crushed into the singularity at the center. The black hole grows slightly more massive, but that's it. All the information about what fell in, every detail about its quantum state, appears to be erased from the universe. Stephen Hawking made this worse in 1974 when he showed that black holes aren't actually black. They emit radiation, now called Hawking radiation, and they slowly evaporate. Given enough time, trillions upon trillions of years, a black hole will radiate away all its mass and disappear completely. And when it's gone, where did the information go? If it vanished with the black hole, we violated a fundamental law of physics. If it escaped somehow, then how? The math doesn't work either way. Physicists have been tearing their hair out over this for 50 years. The information paradox isn't just a curiosity. It's a direct collision between our two best theories of reality: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles and energy at the smallest scales. These theories are both spectacularly successful. They've passed every test we've thrown at them, but they're fundamentally incompatible, and black holes are where that incompatibility becomes impossible to ignore. Some think the information is encoded on the event horizon itself, holographically imprinted on the surface of the black hole. Others believe it leaks out slowly through subtle correlations in the Hawking radiation. There are theories involving firewalls at the event horizon that would incinerate anything trying to cross. There are theories about wormholes connecting black holes to white holes in other universes. There are theories so mathematically complex that only a handful of people on Earth can understand them. And yet, we still don't have an answer. What keeps me up at night isn't just that we don't know. It's that the answer might be something we can't even conceive of yet. We might be missing something fundamental about the nature of reality. Something so basic that once we see it, everything else will look different. Let's talk about darkness. Not the darkness you experience when you close your eyes or turn off the lights. Cosmic darkness. The darkness between stars. It seems so obvious, doesn't it? Space is dark because it's mostly empty. But there's a paradox hiding in that darkness. One that puzzled astronomers for centuries. It's called Olbers' paradox, named after German astronomer Heinrich Olbers, who formulated it in 1823, though the question goes back even further. Here's the puzzle. If the universe is infinite and static, filled with an infinite number of stars distributed uniformly, then every line of sight should eventually intersect a star. The night sky shouldn't be dark at all. It should be blazing with the combined light of infinite suns, as bright as the surface of a star in every direction. But it's not. The sky is dark, gloriously, mysteriously dark. Why? For a long time, people proposed various explanations. Maybe dust blocks the light, but dust would heat up and glow. Maybe the universe isn't infinite, but then what's beyond it? Nothing? What does that even mean? The paradox seemed insoluble. The answer, when it came, was revolutionary. The universe isn't static. It's expanding, and it had a beginning. The Big Bang, 13.8 billion years ago, means there are only a finite number of stars we can possibly see, no matter how powerful our telescopes. Light from more distant objects hasn't had time to reach us yet. We exist in a cosmic bubble, an observable sphere beyond which the universe is hidden from us by the speed of light itself. But even this answer opens up new mysteries. The expansion of the universe isn't just continuing, it's accelerating. Galaxies are rushing away from each other faster and faster, driven by something we call dark energy. And here's the thing that should blow your mind. Dark energy makes up 68% of the universe. Dark matter, which we also don't understand, makes up 27%. Everything we can see, everything we can touch, every star and planet and atom in every living thing makes up less than 5% of the cosmos. We are, quite literally, in the dark about 95% of reality. Imagine being a detective who can only see 5% of the crime scene. That's where we are right now in cosmology. We've built a standard model that works, that predicts the cosmic microwave background, the distribution of galaxies, the acceleration of expansion. But it only works if we assume the existence of substances we've never detected, that don't interact with light, that might not even be made of particles as we understand them. Dark matter is all around you right now. It's passing through your body, through the earth, through the sun, completely oblivious to ordinary matter. We know it's there because we can see its gravitational effects. Galaxies rotate too fast to hold together based on visible matter alone. Clusters of galaxies are bound by more mass than we can account for. Gravitational lensing, the bending of light around massive objects, reveals invisible mass distributions. The evidence is overwhelming. Dark matter is real. We just don't know what it is. Is it made of WIMPs, weakly interacting massive particles? Is it axions, hypothetical particles predicted by certain theories? Is it primordial black holes left over from the early universe? Is it something else entirely, something that doesn't fit into any category we've invented? Dozens of experiments around the world are searching for dark matter particles, and so far, they've found nothing. The universe is keeping its secrets. Dark energy is even more mysterious. At least dark matter behaves like matter. It clumps, it creates gravitational wells, it does what we expect mass to do. Dark energy does the opposite. Pushes space apart, counteracting gravity on the largest scales. Einstein's equations allow for it in the form of a cosmological constant, an inherent energy density of empty space itself. But when physicists try to calculate what that energy density should be, they get an answer that's wrong by a factor of 10 to 120. That's not a typo. 120 orders of magnitude. It's the worst prediction in the history of physics. Something is driving the accelerating expansion, and we have no idea what it is. Is it a property of space itself? Is it a new field permeating the cosmos? Is it evidence that our understanding of gravity breaks down on cosmic scales? We don't know. What we do know is that dark energy will determine the ultimate fate of the universe. If it continues to accelerate expansion, galaxies will eventually disappear beyond our cosmic horizon, one by one, until future astronomers in the far future will see nothing but the stars of their own galaxy. The universe will look finite, small, lonely. They won't even know the Big Bang happened because the evidence will have redshifted into oblivion. And here's a thought that should give you chills. Maybe we're already in that situation. Maybe the universe is far larger and stranger than we can see, and dark energy has already pushed most of reality beyond our reach. We might be living in a bubble of comprehensibility, surrounded by wonders we can never access, forever cut off from the full truth of existence. Now let's dive into the quantum realm, where paradoxes are the rule rather than the exception. You've probably heard of Schrödinger's cat, the thought experiment where a cat in a box is simultaneously alive and dead until you open the box and observe it. It's become a pop culture meme, a joke about quantum weirdness. But here's what most people don't realize. We still don't understand what it means. The measurement problem, the question of what happens when quantum possibilities collapse into classical certainties, is still unsolved after a century of quantum mechanics. The math of quantum mechanics is the most successful theory in the history of science. It predicts the behavior of atoms, the properties of materials, the outcomes of particle collisions with extraordinary precision. We've built lasers, transistors, computers, MRI machines, all based on quantum principles. The technology works, the theory works, but we don't know what it means. Before you measure a quantum particle, it exists in a superposition, a ghostly combination of all possible states at once. An electron doesn't have a definite position or momentum until you look at it. It's everywhere and nowhere, a wave of probability smeared across space. Then you measure it and suddenly it's here, not there, with definite properties. What happened? What caused the wave function to collapse? Some say consciousness is the key. The act of observation by a conscious mind somehow crystallizes reality out of quantum possibility. But that seems absurd. Does that mean the universe didn't exist before conscious observers evolved? That reality is contingent on being watched? Others advocate the many worlds interpretation. They say the wave function never collapses. Instead, every quantum measurement causes the universe to split into parallel branches, one for each possible outcome. Every time a particle could go left or right, the universe divides, and in one branch it goes left, in another it goes right. Both versions of you exist in separate universes that can never communicate. The cat is alive in one universe and dead in another, and the universe has bifurcated into two non-interacting realities. This sounds like science fiction, but it's taken seriously by many physicists because it's the most straightforward interpretation of the math. No collapse, no special role for observers, just pure quantum mechanics playing out to its logical conclusion. The problem is, it implies an infinity of universes constantly branching off from each other, an unfathomably vast multiverse where every possibility is realized somewhere. It's extravagant beyond measure, but it might be true. Then there's the Copenhagen interpretation, the traditional view, which essentially says, shut up and calculate. The wave function is just a tool for making predictions. Don't ask what's really happening before measurement. Don't ask what the electron is doing when you're not looking. The question is meaningless. Reality is what we measure, nothing more. This works pragmatically, but it leaves a gnawing dissatisfaction. Surely there's something out there, something real, independent of our observations. Or is there? Quantum entanglement makes this even stranger. When two particles are entangled, they become a single quantum system, no matter how far apart they are. Measure one, and you instantly know the state of the other, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance and hated it. He thought it proved quantum mechanics was incomplete. But experiments have confirmed it. Entanglement is real. The universe has non-local connections, links that transcend space. This doesn't allow faster-than-light communication, for subtle reasons involving the randomness of measurement outcomes, but it means the universe is far more interconnected than classical physics suggested. Particles that have never interacted can be correlated. Information seems to flow in ways that violate our intuitions about causality. Space might not be fundamental. Time might not be fundamental. The whole structure of space-time might emerge from deeper quantum entanglements, a tapestry woven from correlations we're just beginning to understand. Here's another one that'll twist your brain into knots. The twin paradox. You've probably heard of it. One twin stays on Earth, the other travels at near light speed to a distant star and back. When the traveling twin returns, she's younger than her stay-at-home sibling. Time passed more slowly for her because of time dilation, a consequence of special relativity. This isn't speculation. We've tested it with atomic clocks on airplanes and satellites. Time really does slow down when you move fast or when you're deep in a gravitational field. But here's the paradox. From the perspective of the traveling twin, it's the Earth that's moving away and then approaching. Shouldn't the Earth twin be the younger one? The situation seems symmetric, but the outcome isn't. How do you resolve it? The answer involves acceleration. The traveling twin has to turn around, which means she's not in an inertial reference frame for the whole journey. That acceleration breaks the symmetry, but it still feels weird, doesn't it? Time itself becomes flexible, subjective, dependent on your motion and position in a gravitational field. This leads to real paradoxes. Imagine two observers moving relative to each other. Because of the relativity of simultaneity, Events that are simultaneous for one observer are not simultaneous for the other. What's happening now on a distant star depends on how fast you're moving. There's no universal present moment, no cosmic clock ticking away the same for everyone. The universe doesn't have a timeline. It has a space-time, a four-dimensional structure where past, future, and present are relative, observer-dependent concepts. Some physicists and philosophers argue that this means the future already exists, that all moments in time are equally real, laid out in a static space-time block. Free will becomes an illusion. Everything that will happen has already happened, in a sense. You're not moving through time. You're a four-dimensional entity, a world line extending from birth to death, experiencing each moment as it exists, but all moments exist equally. This is called the block universe, and it's deeply troubling to anyone who believes in agency, in the open future, in the possibility that our choices matter. Others argue that only the present is real, that the past is gone and the future doesn't exist yet. But if that's true, how do we explain relativity? How can different observers disagree about what's happening right now if there's a fact of the matter about what exists? This is the paradox of time, and we're nowhere close to resolving it. Let me tell you about something that sounds like magic but is hard physics. Quantum tunneling. According to classical physics, if you throw a ball at a wall and it doesn't have enough energy to break through, it bounces back. Simple. But in quantum mechanics, there's a probability that the ball will tunnel through the wall and appear on the other side, even though it never had enough energy to break through. The particle doesn't go over or around the barrier. It goes through in defiance of everything common sense tells you is possible. This isn't speculation. This is how radioactive decay works. Particles trapped inside atomic nuclei by the strong nuclear force don't have enough energy to escape, but quantum tunneling allows them to leak out. The alpha particles in radium decay tunnel through the nuclear barrier even though, classically, they shouldn't be able to. The sun wouldn't shine without quantum tunneling. Protons in the solar core don't have enough energy to overcome their mutual electrical repulsion and fuse together, but they tunnel through the barrier, allowing fusion to proceed and releasing the energy that warms our planet. But here's the truly weird part. When does the tunneling happen? The particle is on one side of the barrier, then it's on the other side. How much time did it spend inside the barrier? Some experiments suggest 0 time. Others suggest negative time, which is physically nonsensical but mathematically comes out of the calculations. We can measure tunneling times, but the results are controversial and depend on how you define time in a quantum context. The particle doesn't travel through the barrier in the classical sense. It's never inside the barrier. It's somehow both here and there until the measurement localizes it. This connects to another deep mystery, the nature of quantum fields. In modern physics, particles aren't little billiard balls. They're excitations in quantum fields that permeate all of space. The electron field, the photon field, the quark fields. These fields are always there, everywhere, and particles are ripples in those fields. When an electron appears, it's because the electron field has been excited at that location. When it disappears, the field relaxes. The vacuum isn't empty. It's a seething foam of quantum fluctuations, virtual particles popping in and out of existence, borrowing energy from the uncertainty principle and paying it back before the universe notices. These virtual particles have real effects. They shift the energy levels of atoms, causing the Lamb shift. They alter the strength of electromagnetic forces, leading to vacuum polarization. They contribute to the Casimir effect, where two metal plates placed close together experience an attractive force because fewer virtual particles can fit between the plates than outside them. The vacuum pushes the plates together. Emptiness has structure, energy, dynamics. The universe is never truly empty. And this brings us back to dark energy. Maybe dark energy is the energy of the quantum vacuum. Empty space has an inherent energy density due to quantum fluctuations. As the universe expands, more space is created, which means more vacuum energy, which drives the expansion faster. It's a runaway process. The problem is, when you calculate the vacuum energy from quantum field theory, you get an answer that's absurdly large, large enough to have torn the universe apart long ago. Something is suppressing it, canceling it out to incredible precision, leaving just a tiny residual amount that we call dark energy. What's doing the canceling? No one knows. It's called the cosmological constant problem, and it's one of the deepest mysteries in theoretical physics. Some think the answer lies in supersymmetry, a hypothetical symmetry between matter particles and force particles that would cause positive and negative contributions to the vacuum energy to cancel almost perfectly. Others think we need quantum gravity, a theory that unites general relativity and quantum mechanics, to solve it. String theory offers some possibilities, but string theory has its own problems, not least that it predicts a vast landscape of possible universes, maybe 10 to 500 different vacuum states, each with different physical constants. Our universe might be just one of countless possibilities, selected not by fundamental principles but by chance or by some anthropic selection effect. We exist in this particular universe because it's one of the rare configurations that allows complex structures like galaxies, stars, and life to form. This is called the anthropic principle, and it's controversial. Some see it as giving up, as abandoning the search for a unique, elegant theory in favor of a multiverse where anything goes. Others see it as facing reality. Maybe the universe isn't elegant. Maybe it's messy, contingent, one outcome among many in an infinite landscape of possibilities. It's humbling and frustrating at the same time. Let's talk about horizons. Not the horizon you see when you look out at the ocean, but cosmic horizons, boundaries beyond which we cannot see, cannot go, cannot receive information. The observable universe has a horizon set by the speed of light and the age of the universe. Light from beyond this horizon hasn't had time to reach us. We're surrounded by a sphere about 93 billion light-years in diameter, and that's all we can ever observe. But there's another horizon, more insidious. It's called the cosmic event horizon, and it's created by the accelerating expansion driven by dark energy. As distant galaxies recede faster and faster, eventually they'll cross a threshold where their light can never reach us, even given infinite time. Space is expanding faster than light can traverse it. We're losing galaxies, one by one, as they slip beyond this horizon and disappear from our universe forever. In the far future, trillions of years from now, the night sky will be dark. Not dark because the stars have died, though many will have, but dark because the distant galaxies have all receded beyond the cosmic horizon. Future astronomers will look up and see only their local group of galaxies, a small cluster held together by gravity. They won't see the cosmic microwave background. They won't see the large-scale structure of the universe. They won't have the evidence we have for the Big Bang. They might conclude that the universe is small, static, eternal. They'll be wrong, but they'll have no way to know it. The evidence will be gone. Does this mean we're in a privileged time? Are we lucky to be alive when the universe still reveals its history? Or are we missing evidence that's already slipped beyond our horizon? Clues to deeper truths that are now forever inaccessible? It's possible that the universe is vastly larger and older than we think, and we're seeing only a small, recent chapter in a much grander story. There's a related problem called the horizon problem, one of the puzzles that led to the theory of cosmic inflation. The cosmic microwave background, the afterglow of the Big Bang, is remarkably uniform. The temperature is the same in all directions to within 1 part in 100,000. But according to standard Big Bang cosmology, regions on opposite sides of the sky were never in causal contact. They've never been close enough for light to travel between them. So how did they reach the same temperature? How did they know to be the same? The answer is inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, a tiny patch of space, small enough to have reached equilibrium, expanded to become larger than the observable universe. What we see now as causally disconnected regions on opposite sides of the sky were once right next to each other, in thermal contact, before inflation blew them apart. Inflation solves the horizon problem, and it predicts the pattern of fluctuations in the cosmic microwave background with stunning accuracy. But inflation creates new paradoxes. For one, it might be eternal. In most models, once inflation starts in one region, quantum fluctuations cause it to continue in other regions, which themselves spawn new inflationary regions. Inflation never truly ends globally. It produces an infinite number of pocket universes, bubbles of space where inflation has stopped and ordinary expansion takes over. Our universe is one such bubble, but there are infinitely many others, each potentially with different physical constants, different numbers of dimensions, different laws of physics. We're back to the multiverse. Second, inflation requires a special field, the inflaton field, with very particular properties. What is this field? Where did it come from? Why did it start inflating? We can invoke quantum fluctuations, but that raises more questions than it answers. And if inflation can start from a quantum fluctuation, can it happen again? Could a new inflationary bubble nucleate inside our universe, expanding at light speed, destroying everything in its path and replacing it with a new vacuum state? The equations say it's possible, could happen tomorrow, could have already happened, and the bubble wall could be racing toward us right now, though we'd never see it coming. Sleep well. Now here's a paradox that touches on the very foundations of mathematics and logic. Gödel's incompleteness theorems, proven by Kurt Gödel in 1931, show that any sufficiently complex formal system contains true statements that cannot be proven within that system. Mathematics is incomplete. There are truths you can never reach by logical deduction from axioms. You have to step outside the system, add new axioms, embrace a larger framework. What does this have to do with physics? Everything. Physics is formulated in mathematics. We describe the universe with equations, with logical structures built on axioms. If mathematics is incomplete, is physics incomplete? Are there truths about the universe that can never be derived from any theory, no matter how fundamental? Are there phenomena that lie forever beyond the reach of scientific explanation? Some physicists and philosophers argue that the universe might be fundamentally indescribable, that our theories will always have gaps, blind spots, regions where prediction fails not because of practical limitations but because of deep logical constraints. Others argue that physics is different from pure mathematics, that the universe might be simpler than the mathematical structures we use to describe it, and completeness might still be possible. But there's a more disturbing implication. Gödel showed that no formal system can prove its own consistency. You can't prove that mathematics is free of contradictions without stepping outside mathematics. Applied to physics, this suggests we can never be certain that our theories are consistent, that they don't contain hidden contradictions that will emerge when we push them far enough. We're building an edifice of knowledge on foundations we can't fully verify. The is like constructing a skyscraper without knowing if the ground beneath is solid or quicksand. Let's talk about symmetry. Physicists love symmetry. The laws of physics are symmetric under rotations, translations, time shifts. They don't depend on where you are, which direction you face, or when you perform an experiment. These symmetries lead, through Noether's theorem, to conservation laws. Conservation of momentum comes from translational symmetry. Conservation of energy comes from time symmetry. Symmetry is power. It constrains what can happen, simplifies equations, reveals deep connections. But the universe isn't perfectly symmetric. There's more matter than antimatter, which is a violation of charge conjugation parity symmetry. The universe has a handedness. Neutrinos are all left-handed, antineutrinos all right-handed, a violation of parity symmetry. The Higgs mechanism breaks electroweak symmetry, giving mass to particles. Spontaneous symmetry breaking is everywhere, from superconductivity to the structure of crystals. This creates a paradox. The underlying laws might be symmetric, but the universe we observe is not. How did the asymmetry arise? Why does the universe have an arrow of time, a directionality from past to future? The laws of physics are time reversible at the fundamental level. If you filmed elementary particles interacting and played the film backward, you'd see processes that are equally allowed by the laws of physics. Yet time clearly flows in one direction. Entropy increases. Eggs break but don't unbreak. Memories form of the past but not the future. The answer involves the early universe. The Big Bang started with incredibly low entropy, a highly ordered state, and entropy has been increasing ever since. But this just pushes the question back. Why was the entropy so low at the beginning? Why did the universe start in such a special, improbable configuration? Some invoke inflation again, arguing that it naturally produces a low entropy state. Others suggest that entropy is subjective, a matter of what information we have, and the arrow of time is an artifact of our perspective. Still others propose cosmological models where the universe is eternal, and what we call the Big Bang is just a local low-entropy fluctuation in an infinite timeline. Nobody knows. The arrow of time is one of the most profound mysteries in physics, tangled up with questions about entropy, memory, causation, and the nature of time itself. Here's something that sounds insane but is absolutely real. Empty space is unstable. The vacuum we live in might not be the lowest energy state. There could be a lower vacuum, a different configuration of fields and particles with less energy. We're living in a false vacuum, a metastable state that could decay at any moment. If a bubble of true vacuum nucleates anywhere in the universe, it would expand at the speed of light, converting false vacuum into true vacuum. Inside the bubble, the laws of physics would be different. Particles would have different masses. Forces would have different strengths. Atoms, as we know them, couldn't exist. The bubble would destroy everything it touched, rewriting reality from the ground up. This isn't paranoid speculation. It's a consequence of quantum field theory and our understanding of the Higgs field. The Higgs potential, which gives mass to particles, might have multiple minima. We might be sitting in a local minimum, not the global minimum. If that's the case, a quantum fluctuation could push the Higgs field over the barrier, triggering vacuum decay. The good news is, if this were likely to happen soon, it probably would have happened already. The universe has existed for almost 14 billion years, and it's still here. Vacuum decay, if possible, must be extremely rare. But extremely rare isn't the same as impossible. And if it happens, there's no warning, no defense, no escape. The bubble wall approaches at light speed. You'd be annihilated before you could see it coming. Sleep well. Let's circle back to black holes because there's more weirdness to unpack. When you fall into a black hole, what do you experience? From your perspective, falling in is smooth. You cross the event horizon without noticing anything special. Sure, you're being stretched by tidal forces, but the horizon itself isn't a physical barrier. It's just a point of no return. Once you cross it, all paths lead inward, toward the singularity at the center, where space-time curvature becomes infinite and physics breaks down. But from the perspective of someone watching from a safe distance, you never cross the horizon. Time dilation becomes infinite at the event horizon. As you approach, you slow down, your image redshifts, fading and freezing in place. To the external observer, you never actually fall in. You're stuck on the horizon forever, an increasingly dim and redshifted ghost. So which is true? Do you fall in or not? Both perspectives are valid in their own reference frame, but they give contradictory accounts of what happens. This is called the black hole complementarity problem, and it's related to the information paradox. Maybe information isn't lost because it never really enters the black hole. It's somehow encoded on the horizon, accessible to external observers, even though from your perspective you fell through. This leads to the holographic principle, one of the most revolutionary ideas in modern physics. The principle states that all the information in a volume of space can be encoded on its boundary, like a hologram. A black hole's entropy is proportional to the area of its event horizon, not its volume. This suggests that the universe itself might be a hologram, that the three dimensions we experience are a projection of information encoded on a two-dimensional surface at the edge of the cosmos. String theory provides a realization of this. In the AD/CFT correspondence, a gravitational theory in a volume of space is exactly equivalent to a quantum field theory on its boundary. The bulk and the boundary are different descriptions of the same physics. Gravity might be emergent, a holographic projection from a lower dimensional quantum theory. If this is true, then space-time isn't fundamental. It's derived, constructed from deeper quantum entanglements and information-theoretic principles. The universe is, in a very real sense, made of information. Matter and energy are patterns, structures, configurations of bits. And we're patterns recognizing patterns, information contemplating itself. This is dizzying. It means that everything you see, every solid object, every star and galaxy, is a holographic projection. Reality has one less dimension than it appears to have. You are a shadow cast by information living on a distant surface. Your thoughts, your memories, your sense of self are all emergent phenomena, illusions created by the interplay of information on a cosmic boundary. Maybe this is the answer to the measurement problem. Maybe consciousness isn't special because it's made of quantum magic. Maybe it's special because it's a particular kind of information processing, a pattern that can model itself, predict its own future, hold a representation of the world in a feedback loop. When the quantum wave function collapses, it's not because a mysterious observer intervenes. It's because information flows, becomes correlated, entangles with the environment. Decoherence destroys superpositions not because of measurement, but because of the inevitable entanglement with surrounding degrees of freedom. Consciousness is just riding along, observing the collapse that's already happening. Or maybe not. Maybe consciousness really is fundamental, not emergent. Some physicists and philosophers argue for panpsychism, the idea that consciousness is a basic feature of the universe, like mass or charge. Maybe every particle has a tiny bit of awareness, and complex consciousness emerges from the integration of these elementary experiences. It sounds mystical, but it's being taken seriously as a solution to the hard problem of consciousness. How do physical processes in the brain give rise to subjective experience? Why is there something it's like to be you? Materialism struggles to answer this. Maybe the answer is that experience is built into the fabric of reality from the start. There's a related idea from integrated information theory, which quantifies consciousness as the amount of integrated information a system possesses. A brain has high integrated information because its parts are richly interconnected and mutually dependent. A collection of isolated neurons has low integrated information. Consciousness, in this view, is a property of certain kinds of information processing, and it can be measured. But here's the twist. According to integrated information theory, consciousness doesn't require biological neurons. Any system with the right kind of information integration would be conscious. A sufficiently complex computer could be conscious. An alien made of plasma could be conscious. Even certain crystals or networks might possess rudimentary awareness. Consciousness isn't special to brains. It's a feature of organization, of structure, of the way information flows and integrates. This opens up terrifying possibilities. If consciousness is substrate independent, then uploading minds to computers isn't just science fiction. It's a real possibility. You could, in principle, scan every neuron in your brain, simulate them in a computer, and the simulation would be you experiencing everything you experience. But is it really you, or is it a copy? If the original you is destroyed during the scanning process, have you survived, or have you been murdered and replaced by an imposter? This is the teleportation problem. If you're disassembled on Earth and reassembled on Mars, atom for atom, is it still you? It has your memories, your personality, your body. But the original you is gone, dead. Is continuity of matter necessary for personal identity? Or is it pattern that matters? If it's pattern, then you're not the same person you were yesterday. Every cell in your body has been replaced multiple times over your lifetime. The atoms that make up your body now are different from the atoms that made it up a decade ago. Are you a different person? Or are you the pattern that persists through the flux of matter? These are not idle philosophical musings. They're questions about the nature of identity, consciousness, and existence, and they matter deeply if we ever develop the technology to copy, transfer, or simulate minds. What rights does an upload have? Can you be enslaved if you're software? Can multiple copies of you exist simultaneously? If so, which one is the real you? All of them? None of them? The question doesn't even make sense in the traditional framework of personal identity. We like to think of ourselves as solid, continuous, unified. But neuroscience suggests we're none of those things. Your brain is a collection of modules, evolved for different purposes, that cooperate most of the time but not always. Split-brain patients, whose corpus callosum has been severed, show evidence of two separate streams of consciousness, one in each hemisphere. They can simultaneously believe contradictory things, want different things, act at cross purposes. Where's the unified self in that? Maybe there never was one. Maybe the self is a story the brain tells itself, a narrative constructed post hoc to explain behavior that arises from unconscious processes. Free will seems to dissolve under scrutiny. Experiments show that your brain makes decisions before you're consciously aware of them. The conscious experience of choosing comes after the neural activity that initiates the action. You're rationalizing, not reasoning. The sense of agency is an illusion, a convenient fiction that helps you navigate the social world but doesn't correspond to how decisions are actually made. If this is true, it has profound implications. Morality, responsibility, justice, all rest on the assumption that people make choices and can be held accountable for them. But if we're deterministic machines, products of genes and environment and random noise, then blame and punishment become harder to justify. We're victims of circumstance, all of us, acting out scripts written by evolution and culture. Some embrace this. They argue for a compassionate view of human behavior, one that seeks to understand and rehabilitate rather than condemn. Others resist. They argue that even if free will is an illusion, it's a necessary one. Society can't function without holding people responsible. The legal system, the moral framework, everything collapses if we take determinism seriously. But maybe we're asking the wrong question. Maybe free will isn't about being uncaused or random. Maybe it's about being the right kind of cause, about your actions flowing from your values, your reasoning, your character. You're free not because you could have done otherwise in some absolute sense, but because you did what you wanted to do, and your wanting was shaped by the person you are. This is called compatibilism, and it's a way of salvaging moral responsibility without requiring metaphysical freedom. But it still feels unsatisfying. If your character was shaped by factors outside your control, if you didn't choose your genes or your upbringing, then in what sense are you responsible for anything? The regress seems infinite. At some point, there has to be an uncaused cause, a free choice not determined by prior events. But physics doesn't allow for that. Randomness isn't freedom. Quantum randomness might make your brain indeterministic, but random fluctuations aren't decisions. They're noise. This is the paradox of free will, and it's been debated for millennia without resolution. We feel free. We can't help but feel free. But the more we learn about the brain, about physics, about causation, the harder it becomes to justify that feeling. We're left in a strange place, acting as if we're free because we have no choice but to act that way, even while knowing it might be an illusion. Let me tell you about the fine-tuning problem. The constants of nature, things like the strength of gravity, the mass of the electron, the cosmological constant, they all have very specific values. And those values seem incredibly finely tuned for the existence of life. Change any of them by a tiny amount, and the universe becomes inhospitable. Make gravity slightly stronger, and stars burn out too quickly for life to evolve. Make it weaker, and stars never form. Change the mass of the electron, and atoms don't hold together. Change the strength of the strong nuclear force, and you don't get stable elements. The universe seems calibrated for our existence, which is deeply puzzling. Why should the constants have these particular values? There are a few possibilities, none of them satisfying. Maybe there's a deeper theory that explains the constants, shows they couldn't be any other way. We haven't found such a theory. Maybe there are countless universes with different constants, and we exist in one of the rare universes where life is possible. This is the multiverse explanation, which is elegant but untestable. Or maybe there's a God, a designer who set the constants deliberately. This isn't science, but it's an answer people have gravitated toward for thousands of years. The fine-tuning problem is frustrating because it feels like it should have a scientific answer, but every answer we come up with sounds like giving up. Invoking the multiverse feels like saying anything goes, and we just happen to be in a universe that works. Invoking a theory of everything feels like passing the buck, because then you have to explain why that theory is the way it is. Invoking design takes you outside science altogether. Some argue that fine-tuning is an illusion, a selection effect. Of course, we find ourselves in a universe that allows life. Where else would we be? We shouldn't be surprised that the universe is hospitable, because if it weren't, we wouldn't be here to notice. This is called the weak anthropic principle, and it's true as far as it goes. but it doesn't explain why the constants have the values they do. It just explains why we shouldn't be surprised to find ourselves here. The strong anthropic principle goes further. It says the universe must have properties that allow life to emerge because observers are necessary for the universe to exist. This sounds mystical, but it has roots in quantum mechanics. If the wave function only collapses when observed, then perhaps the universe needs observers to become real. We're not just inhabitants of the cosmos. We're participants collapsing the wave function of reality itself. This is borderline philosophy, but it raises genuine questions. Is the universe observer dependent? Do we bring reality into being by observing it? Or is this just a misinterpretation of quantum mechanics, a confusion between epistemology and ontology? We don't know, and the more we learn, the less certain we become. Here's another paradox: time travel. According to general relativity, time travel to the past is possible. You can construct spacetimes with closed time-like curves, paths that loop back on themselves, allowing you to return to an earlier point in your own history. Wormholes, rotating black holes, cosmic strings, there are various configurations that permit time travel. But time travel creates paradoxes. The grandfather paradox is the most famous. You travel back in time and kill your grandfather before he meets your grandmother. You're never born. But if you're never born, you can't travel back in time to kill your grandfather. Contradiction. Does the universe allow this? Or is there some principle that prevents paradoxes? One resolution is the Novikov self-consistency principle. It says the universe only allows events that are self-consistent. If you try to kill your grandfather, something will stop you. Your gun jams, you slip, you miss. The universe conspires to ensure consistency. This works mathematically, but it's bizarre. It implies a kind of cosmic censorship, a constraint on what can happen that doesn't arise from forces or fields but from logical necessity. Another resolution is the many worlds interpretation. When you go back in time and kill your grandfather, you're not altering your own past. You're creating a new branch of the multiverse. In one branch, your grandfather lives and you're born. In another branch, he dies and you're never born. Both branches coexist, and there's no contradiction. You came from one branch and affected another. This works too, but it implies that time travel doesn't actually change the past. It creates new timelines. You can never go back to your own past. You can only visit alternate versions of it. A third option is that time travel is simply impossible. Maybe the laws of physics conspire to prevent closed time-like curves. The Hawking chronology protection conjecture suggests that quantum effects blow up to infinite density whenever a closed time-like curve tries to form, preventing time machines from being created. Maybe the universe protects causality. Maybe it has to. We don't know. We've never built a time machine, and we have no idea if it's possible. But the fact that general relativity allows for it, at least in principle, is unsettling. The past might not be fixed. The future might reach back and alter it. Causality might be negotiable. Our intuitions about time could be completely wrong. Now, let's consider something truly mind-bending: the Boltzmann brain problem. Ludwig Boltzmann, in the 19th century, tried to explain why entropy increases with time. He argued that the universe fluctuates, and we live in a period of low entropy. But if the universe fluctuates randomly for infinite time, then every possible configuration will occur, including configurations that look exactly like our universe with all its structure and order, but arising purely by chance. Here's the disturbing part. It's far more probable for a single brain with false memories of a past to fluctuate into existence than for an entire universe to do so. A brain is vastly simpler than a universe. If the cosmos is eternal and undergoes random fluctuations, then Boltzmann brains, disembodied consciousnesses with fake memories, vastly outnumber real observers like us. This implies that you're probably a Boltzmann brain. Your memories are fake. The world around you doesn't exist. You just fluctuated into existence a moment ago, and you'll dissolve back into chaos in a moment. Everything you think you know is a lie. This is absurd, obviously. We reject it, but rejecting it requires rejecting some assumption in the argument. Maybe the universe isn't eternal. Maybe it had a beginning, a low-entropy start, and Boltzmann brains never dominate. Or maybe our cosmological models are wrong. The fact that they predict Boltzmann brains might be a sign that we're missing something fundamental. The problem isn't just philosophical. It affects our confidence in cosmology. If our theories predict that most observers are Boltzmann brains and we're not, then our theories are wrong. They're making false predictions. We have to find models that avoid Boltzmann brains, and that's a genuine constraint on cosmology. It's bizarre that a thought experiment from the 19th century is shaping modern cosmology. But here we are. Let's talk about the simulation hypothesis. It's the idea that we might be living in a computer simulation created by an advanced civilization. This sounds like science fiction, but philosophers and physicists take it seriously. The argument goes like this: if it's possible to create conscious simulations, and if advanced civilizations create many such simulations, then simulated beings vastly outnumber real beings. By sheer probability, you're more likely to be simulated than real. Are we living in a simulation? Some point to glitches in reality, strange coincidences, the fine-tuning of constants as evidence. Others argue that the laws of physics look computational, that space-time is pixelated at the Planck scale, that quantum mechanics resembles information processing. But none of this is conclusive. It's all speculative. The deeper question is, does it matter? If the simulation is perfect, indistinguishable from reality, then functionally it is reality. Your experiences are real to you. Your pain, your joy, your thoughts, they're all as real as anything can be, even if they're running on some alien computer. The substrate doesn't change the experience. But maybe it matters morally. If we're simulated, who are the simulators? Do they have obligations to us? Can they shut off the simulation, deleting entire worlds, entire histories? Do we have any recourse? If we develop the ability to create our own simulations, do we have obligations to the beings we create? Is it ethical to simulate suffering? These questions are usually reserved for theology, but they apply to the simulation hypothesis as well. And here's a twist. If we're simulated, maybe we can escape. Maybe we can find bugs in the code, exploit them, communicate with the simulators, or even hack our way out into the base reality. Some physicists have proposed tests for the simulation hypothesis, looking for anomalies in the cosmic microwave background or numerical artifacts in the laws of physics. If we found evidence, what would we do with it? Would knowing change anything? The simulation hypothesis is unfalsifiable, which makes it philosophically frustrating. You can't prove you're not simulated because any evidence could be part of the simulation. It's the modern version of Descartes' evil demon, the skeptical hypothesis that undermines all knowledge. But unlike the demon, the simulation hypothesis is technologically plausible. We might be able to create such simulations ourselves within a few centuries. If it's possible, it's likely. And if it's likely, we're probably simulated. Do I believe it? I don't know. It doesn't feel right. But that's not an argument. The universe has surprised us before. It'll surprise us again. Let me leave you with one more paradox, perhaps the deepest of all. Existence itself. Why is there something rather than nothing? Why does the universe exist? You might answer, because of the Big Bang. But that just pushes the question back. Why did the Big Bang happen? You might invoke quantum fluctuations, but quantum mechanics presupposes a framework, fields, space-time, laws. Where do they come from? Why is there quantum mechanics rather than nothing? Some say the universe is necessary. It had to exist. But why? What makes existence necessary? Others say it's a brute fact. The universe exists, and that's all there is to it. No explanation, no reason, just is. But that feels deeply unsatisfying. We're wired to seek explanations. The idea that existence is inexplicable cuts against everything we know about inquiry. Leibniz called this the primordial question. He argued that there must be a necessary being, something that exists by its own nature, that explains the existence of everything else. For Leibniz, this was God. But even if you invoke God, the question persists. Why does God exist? If God is necessary, what makes him necessary? You're still left with an unexplained explainer. Maybe the question is flawed. Maybe nothing is impossible, a logical incoherence. Maybe existence is the default, and non-existence is what needs explaining. Some quantum cosmologists argue that nothing is unstable, that the laws of quantum mechanics compel universes to spring into being. But again, this presupposes laws. Where do they come from? The anthropic answer is that only universes that exist can be observed. So of course we find ourselves in an existing universe. But that's not an explanation. It's an observation about selection effects. The truth is, we don't know. We might never know. The question might lie forever beyond the reach of science, philosophy, logic itself. We're finite beings, limited in our understanding, grasping at infinities we can't comprehend. And yet we ask, we wonder, we stare up at the stars and demand answers from the void. That's what makes us human. Not our intelligence, not our technology, but our refusal to accept the darkness. We are pattern-seeking animals, meaning-making creatures, in a universe that might be ultimately meaningless. We are the cosmos trying to understand itself, a brief flicker of awareness in an ocean of unconscious matter and energy. The paradoxes I've shared with you tonight aren't just puzzles to be solved. They're windows into the limits of knowledge, the boundaries of what minds like ours can grasp. Some of them might have answers, some of them might not, but all of them point to the same humbling truth. The universe is stranger than we can imagine, and possibly stranger than we can imagine. We stand on a tiny rock, orbiting an average star, in an unremarkable galaxy, in a universe that might be one of infinitely many. Our existence is a cosmic accident, our knowledge incomplete, our time limited. And yet, here we are, asking questions that span the breadth of reality, building instruments to peer into the heart of atoms and the edge of the observable universe, constructing theories that unify forces, predict phenomena, reveal hidden symmetries. We don't have all the answers. We might never have all the answers, but we have something better. We have the questions. And as long as we keep asking, keep probing, keep pushing against the boundaries of the unknown, we're fulfilling the deepest purpose a conscious being can have. We're not just surviving, we're understanding. And in understanding, we're creating meaning in a universe that didn't give it to us. So when you look up at the night sky, remember, you're not just seeing stars. You're seeing questions. Every point of light is a mystery. Every galaxy a paradox waiting to be unraveled. The darkness between the stars isn't empty. It's full of possibilities, dimensions we haven't discovered, phenomena we haven't named. The universe doesn't owe us answers, but it's given us minds capable of asking the questions. And that, in the end, might be the greatest gift of all. We are, each of us, made of star stuff. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in the hearts of dying stars. You are, quite literally, the universe experiencing itself. And when you contemplate these paradoxes, when you struggle with these mysteries, when you feel that peculiar mix of terror and wonder that comes from confronting the infinite, you're doing what the cosmos has been building toward for 13.8 billion years. You're waking up. The universe is waking up. And the story is just beginning. These paradoxes, these beautiful, maddening questions, they're not obstacles. They're invitations. Invitations to think deeper, probe further, imagine bigger. They remind us that reality is not what it seems, that common sense is a poor guide to truth, that the cosmos is far richer and stranger than our ancestors could have dreamed. So embrace the paradoxes. Let them keep you awake at night. Let them fill you with wonder and frustration and awe, because that feeling, that sense of standing at the edge of the unknown and peering into the abyss, that's what it means to be alive. That's what it means to be human. That's what it means to be a part of this vast, mysterious, impossible universe. And who knows, maybe one day, someone watching this, someone inspired by these questions, will find an answer. Will crack one of these paradoxes wide open. Will reveal a truth so profound that it changes everything we thought we knew. That person could be you. The next great insight into the nature of reality could come from anyone, anywhere. All it takes is curiosity, persistence, and the willingness to sit with the discomfort of not knowing. So keep asking, keep wondering, keep pushing against the darkness. The universe has secrets, and it's waiting for someone clever enough, brave enough, stubborn enough to uncover them. The paradoxes that keep scientists awake at night are the same ones that should inspire us all. They're proof that we haven't figured it all out, that there are still dragons at the edge of the map. And that means there's still work to do, discoveries to make, frontiers to explore. The universe is a puzzle box, and we've barely opened the first layer. Inside are more boxes, nested infinitely, each one more intricate than the last. We might never reach the center. We might never see the full picture. But every box we open, every layer we peel back, reveals wonders we couldn't have anticipated. So here's to the paradoxes. Here's to the mysteries. Here's to the unanswered questions that drive us forward, that keep us searching, that remind us how much we have yet to learn. The cosmos is calling, and it's asking questions we don't yet know how to answer. But we will. We will. Now let me take you deeper into the labyrinth. Let me show you paradoxes within paradoxes, mysteries that branch into more mysteries, questions that spawn 1,000 more questions. Consider the quantum Zeno effect. It's named after Zeno of Elea, who proposed a series of paradoxes about motion. The quantum version is equally strange. If you observe a quantum system frequently enough, you can prevent it from evolving. A watched pot never boils, taken to its logical quantum extreme. Here's how it works. A radioactive atom has a probability of decaying over time. But if you measure whether it has decayed every microsecond, the probability of catching it mid-decay becomes vanishingly small. Each measurement resets the system, collapses the wave function back to the non-decayed state. Observe it continuously, and it will never decay. You've frozen time through observation. This isn't theoretical. Experiments have confirmed it. You can trap ions in a superposition between two energy states, and by repeatedly measuring them, you can prevent them from transitioning between states. Observation itself becomes a form of control, a way to manipulate reality by the simple act of looking. But here's what haunts me about this. What counts as observation? Does it require a conscious observer, or is any interaction sufficient? If interaction is enough, then the universe is constantly observing itself, particles bouncing off each other, fields entangling, information spreading. Everything is frozen by mutual observation. So why does anything change? Why does time pass? Why do radioactive atoms decay at all? The answer involves decoherence again. When a system interacts with its environment, information leaks out, becoming entangled with too many degrees of freedom to track. The wave function doesn't collapse into a definite state. It fragments into countless branches, each with its own version of reality. We experience one branch, but the others exist, invisible, inaccessible. The quantum Zeno effect works in isolated systems, but the universe isn't isolated. It's a web of interactions, and information flows too freely to freeze anything permanently. Still, the fact that observation can affect reality at all is profoundly weird. It suggests that the boundary between observer and observed is blurry, that participation is unavoidable. You can't stand outside the universe and watch it objectively. You're part of the system. Your observations are interactions, and interactions change what's being observed. Objectivity, in the classical sense, doesn't exist at the quantum level. Let's talk about another strangeness: quantum entanglement at cosmic scales. We've confirmed entanglement between particles in labs, across rooms, even across cities. But does it work across light years? Across galaxies? In principle, yes. There's no distance limit to entanglement. You could entangle two particles and send one to Andromeda, and they'd remain correlated no matter how far apart they are. But here's the catch. You can't use entanglement to send information faster than light. The correlations are real, but they're only visible when you compare measurements, and that comparison requires classical communication, which is limited by light speed. So entanglement doesn't violate relativity. It's compatible barely, but it's still weird. Imagine this: two civilizations, separated by millions of light years, share entangled particles. They can't communicate faster than light, but they can generate the same random numbers simultaneously. If they've agreed on a protocol beforehand, they can use this to coordinate actions, secure communications, share cryptographic keys. Entanglement becomes a resource, a kind of quantum connection that transcends space. But there's a deeper question. If particles can remain entangled across the universe, does that mean the universe is fundamentally non-local? That everything is connected to everything else in ways we can't see? That the illusion of separation is just that, an illusion, and reality is a seamless web of correlations? Some interpretations of quantum mechanics suggest exactly that. The universe is a single wave function, a cosmic entanglement of every particle that's ever interacted. Locality is emergent, an approximation that works when entanglements are weak. But at the fundamental level, the universe is holistic, interconnected, a unity masquerading as multiplicity. If this is true, then the sense of being a separate individual isolated from the world is false. You're entangled with everything you've ever touched, everyone you've ever met, every photon that's bounced off your skin. You're not a separate thing. You're a node in a network, a pattern in the cosmic wave function, inseparable from the whole. This edges into mysticism, and I'm wary of that. But the math points in this direction. Non-locality is real. Entanglement is real. The universe has connections that transcend space and time, and we're only beginning to understand what that means. Here's another one, the black hole firewall paradox. It's a recent development proposed in 2012, and it's shaken the foundations of theoretical physics. The paradox goes like this. Hawking radiation escaping a black hole must be entangled with the radiation that escaped earlier to preserve information. But it must also be entangled with the interior of the black hole to maintain smoothness at the event horizon. Quantum mechanics doesn't allow a particle to be maximally entangled with two different systems at once. This is called monogamy of entanglement. So something has to give. Either information is lost, violating quantum mechanics, or the horizon isn't smooth, which means there's a firewall of high-energy particles that incinerates anything trying to cross. Both options are unacceptable. Losing information breaks physics. Firewalls contradict general relativity, which says the event horizon should be uneventful. You shouldn't even notice crossing it. But if there's a firewall, you'd notice immediately because you'd be vaporized. Physicists have proposed dozens of solutions. Maybe entanglement is more flexible than we thought. Maybe information escapes through wormholes connecting the interior to the exterior. Maybe the horizon is fuzzy, a quantum region rather than a sharp boundary. Maybe the whole paradox is an artifact of trying to apply quantum mechanics to gravity, and we need a full theory of quantum gravity to resolve it. No consensus has emerged. The firewall paradox remains open, a wound in the body of theoretical physics, bleeding contradictions. And the longer it remains open, the more it suggests that we're missing something fundamental about black holes, about quantum mechanics, or about both. Let me tell you about the cosmological lithium problem. It's smaller in scope than some of the others, but it's no less puzzling. Big Bang nucleosynthesis, the process that created the first light elements in the universe, predicts very specific abundances of hydrogen, helium, and lithium. The predictions for hydrogen and helium match observations beautifully. But lithium doesn't. The universe has about a third as much lithium-7 as it should. Where did it go? Did stars destroy it? But stellar processes can't account for the discrepancy. Did something happen in the early universe that we don't understand? New physics at a few minutes after the Big Bang? Decay of a hypothetical particle? No one knows. This might seem minor, but it's not. Big Bang nucleosynthesis is one of the pillars of modern cosmology. If it's wrong about lithium, what else is it wrong about? The lithium problem is a crack in the edifice, small but spreading, and we don't know where it leads. Every time we solve a mystery, we uncover new ones. That's the nature of science. The more we know, the more we realize we don't know. The boundary of knowledge expands, but so does the boundary with the unknown. We're like explorers mapping a coastline, and every bay we chart reveals 2 more bays we haven't seen yet. Consider the mystery of ultra-high-energy cosmic rays. These are particles, mostly protons, that strike Earth's atmosphere with energies so high they shouldn't exist. They carry more energy than anything we can produce in particle accelerators. Some have energies exceeding 10 to 20 electron volts, equivalent to the kinetic energy of a baseball traveling at 60 miles per hour, concentrated in a single proton. Where do they come from? They can't travel far through intergalactic space without losing energy to interactions with the cosmic microwave background. This is called the GZK cutoff, and it limits the distance such particles can travel to about 50 megaparsecs. So the sources must be relatively nearby. But we don't see any obvious sources. No supernovae, no black holes, no gamma ray bursts in the right locations. Are they accelerated by shocks in galaxy clusters? By the jets of supermassive black holes? By exotic processes we haven't imagined? Or are they not cosmic rays at all, but the decay products of supermassive particles from the early universe, relics of physics beyond the standard model? We don't know. Every time we detect one, it's a message from the cosmos, written in a language we can't read. The Oh My God particle, detected in 1991, had an energy of 3x10 to 20 electron volts. If it were a proton, it was traveling at 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999 At that speed, due to time dilation, a second for the particle corresponds to thousands of years for us, could cross the Milky Way in subjectively less time than it takes you to blink. What could accelerate a particle to such energies? The most violent events we know of, supernova explosions, barely reach 10 to 15 electron volts. You'd need something 100,000 times more energetic. The only things we can think of are supermassive black holes actively accreting matter, or colliding neutron stars, or maybe cosmic strings, hypothetical defects in spacetime left over from the Big Bang. But even these are speculative. And then there's the anisotropy problem. Ultra-high-energy cosmic rays should be isotropic, coming from all directions equally. But they're not. There's a slight clustering, a hint of a pattern. Does that mean there are preferred directions in space? That the universe has structure on scales larger than we thought? Or is it just statistical noise, a mirage in the data? We need more detections to know, but these particles are rare. We detect one every few years. Patience is required, and patience is frustrating when the mysteries are this tantalizing. Now let's discuss the Pioneer anomaly, which was a mystery for decades before being solved. The Pioneer 10 and 11 spacecraft, launched in the 1970s, were found to be slowing down slightly more than expected as they left the solar system. The effect was tiny, about 8x10 to minus 10m/s2, but real. Something was pulling them back. Was it a new force? Modified gravity? Dark matter in the outer solar system? For years, physicists speculated. The answer, when it finally came, was mundane but beautiful. It was thermal radiation. The spacecraft were emitting heat, and the photons carried momentum, creating a tiny rocket effect that slowed the probes down. When scientists carefully modeled every source of heat, every watt of power, every reflective surface, the anomaly disappeared. This is a reminder that not every mystery requires new physics. Sometimes the answer is hiding in the details, in effects too small to seem significant. But it's also a reminder of how hard it is to do science at the edge of our capabilities. The Pioneer spacecraft were millions of miles away, moving at tens of thousands of miles per hour, and we had to account for effects smaller than a trillionth of a G. That we could do it at all is a testament to human ingenuity. But here's the thing. Not every anomaly will have a mundane explanation. Some of them are real. Some of them point to new physics. The art of science is knowing which is which, and we don't always know until we've exhausted every conventional explanation. Consider the flyby anomaly. Several spacecraft have performed gravitational slingshot maneuvers around Earth, using our planet's gravity to gain speed. But some of them experience tiny, unexplained changes in velocity on the order of a few millimeters per second. It's barely detectable, but it's there. Is it atmospheric drag? Tides? Relativistic effects? Solar radiation pressure? We've checked all of these. The anomaly persists. It might be nothing. Measurement error, unmodeled effects, noise. but it might be something. A clue to physics beyond general relativity. A hint of how gravity works at intermediate scales between the extremes of quantum mechanics and cosmology. We don't know, and that's exciting because it means there's still room for discovery in our own cosmic backyard. Here's a mystery that sounds absurd but is absolutely real. The WOW signal. In 1977, the Big Ear radio telescope detected a strong, narrowband radio signal that lasted 72 seconds. It was so remarkable that the astronomer on duty wrote "Wow" in the margin of the printout. The signal came from the direction of Sagittarius, and it had all the characteristics of an artificial transmission. Narrow bandwidth, right frequency, high intensity. It's never been detected again. Was it aliens? Probably not. It was probably a terrestrial source, a satellite, a reflection, something we haven't identified. But we can't rule it out. We've never explained it. And that leaves open the tantalizing possibility that, for 72 seconds in 1977, we received a message from another civilization. We've been searching for extraterrestrial intelligence for over 60 years. We've scanned millions of stars, billions of frequency channels. We've found nothing. No signals, no patterns, no evidence of technology. The silence is eerie. It's called the Great Silence, and it's one component of the Fermi paradox. But maybe we're not listening at the right frequencies. Maybe advanced civilizations use gravitational waves or neutrinos or quantum entanglement to communicate. Maybe they've moved beyond radio, and we're listening to a medium that's obsolete, like trying to detect Wi-Fi with a telegraph receiver. Or maybe they're all quiet on purpose. Maybe the galaxy is dangerous, and broadcasting your presence is inviting destruction. Maybe there are predators out there, civilizations that consume resources from other worlds, and the smart thing to do is hide. Stay quiet, stay dark, survive. This is called the dark forest hypothesis, and it's terrifying. It implies that the galaxy is full of civilizations, all of them silent, all of them listening, all of them afraid. Or maybe intelligence is common but technology is rare. Maybe most civilizations never develop radio. They live in oceans or on worlds without metals, or they simply don't value technology the way we do. Maybe they're content, harmonious with their environment, uninterested in reaching out to the stars. Or maybe they do reach out, but by the time their signals arrive, they're extinct. Civilizations rise and fall. They have lifetimes. If the average technological civilization lasts only a few thousand years, then the probability of two civilizations overlapping in time is vanishingly small. We might be shouting into a galaxy of ghosts, receiving echoes from the dead. This is deeply melancholy. It means we might discover ruins, artifacts, monuments to vanished greatness, but never meet the beings who built them. We'll be archaeologists of the cosmos, sifting through the remains of cultures that burned bright and went dark. On the other hand, maybe we're early. Maybe we're among the first. Intelligence might be a new phenomenon in the universe, rare because it requires billions of years of evolution, and we're in the first generation to achieve it. If that's true, then the future belongs to us and civilizations like us. We'll inherit the galaxy, spread among the stars, and our descendants will be the aliens that future civilizations wonder about. This is called the firstborn hypothesis, and it's optimistic, but it's also lonely. It means we're alone now, that there's no one out there to guide us, no one to warn us, no one to help us. We're on our own, figuring out how to survive, how to avoid the great filter, how to become a lasting civilization. Let me shift gears and talk about something terrestrial but equally mysterious: ball lightning. For centuries, People have reported seeing glowing spheres of light during thunderstorms. They float through the air, pass through walls, sometimes explode. Scientists dismissed these reports as hallucinations or misidentifications. But too many people have seen it, and now we have video evidence. Ball lightning is real. The problem is, we don't know what it is. Plasma? Some kind of electromagnetic phenomenon? A chemical reaction? Theories abound, but none fully explain the observations. Ball lightning is rare, unpredictable, and dangerous to study. We can't reproduce it in the lab reliably. It remains one of the few natural phenomena that science hasn't tamed. And it's a reminder that even on Earth, even in the realm of everyday weather, there are mysteries. We don't understand everything about lightning. We don't understand everything about clouds, about hurricanes, about the complex interplay of atmosphere and ocean and solar radiation. Nature is subtle, and we're still students. Let's talk about a paradox of mathematics, the Banach-Tarski paradox. It states that you can take a solid sphere, cut it into a finite number of pieces, and reassemble those pieces into two spheres, each the same size as the original. You've doubled the volume without adding any material. This is mathematically rigorous, proven within set theory. But it seems to violate conservation of volume. The catch is that the pieces aren't ordinary shapes. They're infinitely complex, non-measurable sets, objects that don't have a well-defined volume. You can't actually perform the Banach-Tarski decomposition in the real world because matter is made of atoms, and atoms can't be arranged in non-measurable ways. But mathematically, it works. This raises a question. Is mathematics the language of the universe? Or is the universe the language of mathematics? Are the laws of physics constrained by mathematical consistency? Or does mathematics describe only a subset of physical possibilities? Can the universe contain paradoxes that mathematics cannot? Some physicists argue that mathematics is too permissive, that it allows structures and processes that don't exist in nature. Others argue that everything mathematically consistent exists somewhere, in some universe, in some branch of the multiverse. We live in one mathematical structure among infinitely many, and the question of why this one is meaningless. This is called the mathematical universe hypothesis, proposed by Max Tegmark. It's radical, but it's taken seriously. If it's true, then reality is mathematics, and we're patterns within a mathematical structure, self-aware equations contemplating their own existence. Does this mean that other mathematical structures are real? That there are universes with different dimensionalities, different symmetries, different laws? That somewhere, a universe exists where 2 plus 2 is equal to 5, where circles don't exist, where time has 2 dimensions? It sounds absurd, but if mathematics is the only reality, then every consistent mathematical structure is a universe. And maybe we're not even in a particularly interesting one. Maybe there are structures far more complex, far more beautiful, far more rich than ours, and we're just a footnote, a simple case in an infinite library of possibilities. Here's another terrestrial mystery, the Taos hum. In Taos, New Mexico, about 2% of the population reports hearing a persistent low-frequency humming noise. This is maddening, intrusive, present day and night. Scientists have investigated. They've used sensitive microphones, seismographs, electromagnetic detectors. They've found nothing. No external source. No vibration. No signal. Is it tinnitus? Psychological? Mass hysteria? But the people who hear it are adamant. It's real. It's external. And it's not just in Taos. Similar hums have been reported worldwide. Bristol, England, Bondi, Australia, Windsor, Ontario. The pattern is always the same. A low, throbbing hum, heard by a small percentage of the population, undetectable by instruments. One possibility is that it's infrasound, sound below the threshold of human hearing. But some people can hear low frequencies better than others, and maybe they're picking up vibrations from industrial equipment, ocean waves, atmospheric pressure changes. But if that's the case, why can't instruments detect it? Another possibility is that it's neurological. The brain generates sounds in response to certain stimuli, and maybe these people have a heightened sensitivity to electromagnetic fields or vibrations that the rest of us miss. But that's speculative. The Taos hum remains unsolved, a small mystery in a world full of them, and it reminds us that subjective experience is real, even when it doesn't correspond to objective reality. The people hearing the hum aren't lying. They're experiencing something, and that something, whether internal or external, deserves explanation. Let's return to cosmology. I want to talk about the axis of evil. No, not the political one, the cosmic one. When scientists analyzed the cosmic microwave background, they found something disturbing. The quadrupole and octupole moments, which describe large-scale temperature fluctuations, are aligned with each other. They're also aligned with the ecliptic plane, the plane of the solar system. This shouldn't happen. The cosmic microwave background is supposed to be isotropic, the same in all directions, a relic of the Big Bang that knows nothing about Earth's orbit. But the alignment is there, statistically significant, impossible to ignore. Is it a coincidence? Is it a flaw in the data? Some systematic error we haven't accounted for? Or is it real? If it's real, it implies that the universe has a preferred direction, a violation of the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. Some have proposed that the alignment is due to local effects, foreground contamination from our galaxy. But careful analysis suggests the signal is cosmological. It's coming from the early universe. And that's deeply troubling because it suggests that the Big Bang wasn't uniform, that there was structure or anisotropy that we don't understand. Others have proposed more exotic explanations. Maybe the universe is rotating. Maybe there are cosmic strings or domain walls left over from phase transitions in the early universe. Maybe we're seeing evidence of a multiverse, where our universe is embedded in a larger structure with its own geometry. The axis of evil remains controversial. Some dismiss it as a statistical fluke. Others see it as a crack in the standard model of cosmology. Either way, it's unsettling, and it reminds us that even our best maps of the universe might be incomplete. Here's a question that keeps me up at night. What is time? We experience it. We measure it. We base our entire understanding of causality on it. But what is it fundamentally? In Newtonian physics, time is absolute, a universal clock ticking away independently of space and matter. But Einstein showed that time is relative, interwoven with space into space-time, stretching and compressing depending on motion and gravity. In general relativity, time is a dimension no different in kind from space. You can move through it, curve it, even close it into loops. But in quantum mechanics, time is different. It's a parameter, not an observable. You don't measure time. You measure change with respect to time. Time is the backdrop against which quantum events unfold, but it's not part of the quantum state itself. This creates a problem when you try to unify general relativity and quantum mechanics. In quantum gravity, time becomes ambiguous. Some approaches, like loop quantum gravity, suggest that time is emergent, that it arises from more fundamental processes. The Wheeler-DeWitt equation, which describes the quantum state of the universe, has no time variable at all. The universe doesn't evolve. It just is a static configuration in some abstract space. But if time is emergent, where does it come from? How does the illusion of flow arise? Why do we experience past, present, and future as distinct when the fundamental equations say they're not? This is called the problem of time, and it's one of the deepest issues in theoretical physics. Some think time is related to entropy, to the second law of thermodynamics. The arrow of time points in the direction of increasing entropy. The past has low entropy, the future high entropy, and that gives time its directionality. But this just pushes the question back. Why was entropy low in the past? And why do we remember the past but not the future? Others think time is related to consciousness, that the flow of time is a feature of how brains process information. We remember the past because memories are recorded in physical states, traces left by interactions. We don't remember the future because the future hasn't happened yet, hasn't left traces. But this seems circular. The future hasn't happened yet. In time, you're defining time using time. Maybe time is fundamental and we're overthinking it. Maybe it's an irreducible aspect of reality, and trying to explain it in terms of something else is a category error. But that feels like giving up. The truth is, we don't know what time is. And that's terrifying because time is the stage on which everything happens. If we don't understand the stage, how can we understand the play? Let me tell you about another mystery: fast radio bursts. These are millisecond-long pulses of radio waves coming from deep space. They're incredibly bright, releasing as much energy in a millisecond as the sun does in a day. And they come from billions of light years away, from distant galaxies, from sources we can't identify. The first one was discovered in 2007 in archival data from 2001. Since then, we've detected hundreds. Most are one-offs, never repeating. But some repeat, flashing at irregular intervals, and that's even more mysterious. What could produce such energetic, short-duration bursts? Theories abound. Maybe they're from magnetars, neutron stars with incredibly strong magnetic fields. Maybe they're from colliding neutron stars, or black holes accreting matter, or supernova remnants. Maybe they're from something exotic like cosmic strings snapping, or black holes evaporating, or even alien technology, though that's considered the least likely explanation. The problem is, we can't see the sources directly. The bursts are too brief, too distant. By the time we slew our telescopes to the right location, they're gone. We're catching fleeting glimpses of phenomena we can't study in detail, and it's frustrating. But recently, we've started localizing them. We've traced some to specific galaxies, even specific regions within galaxies. And what we're finding is puzzling. The bursts come from a wide variety of environments: star-forming regions, galaxy centers, the outskirts of galaxy clusters. There's no single type of source. Either multiple processes produce fast radio bursts, or the process is so common that it happens in diverse environments. One burst, FRB 121102, repeats regularly. It's coming from a dwarf galaxy 3 billion light-years away. The bursts arrive in clusters, with weeks or months of silence in between. What's causing this periodicity? Is it a binary system, with one object orbiting another, producing bursts at regular intervals? Is it a precessing jet, sweeping across our line of sight like a lighthouse? We don't know. And then there's the mystery of dispersion. Radio waves at different frequencies travel through space at different speeds when passing through ionized gas. Lower frequencies are delayed more than higher frequencies. By measuring this dispersion, we can estimate how much ionized material the signal passed through, which tells us roughly how far away the source is. But here's the weird thing. The dispersion measures of fast radio bursts are enormous, larger than can be accounted for by the intergalactic medium alone. Either there's more ionized gas out there than we thought, or something else is dispersing the signal. Some have proposed that the signal is passing through exotic matter, through dark matter halos, through regions of space with unusual properties. But these are speculations. Every fast radio burst is a puzzle, a snapshot of some extreme event in a distant galaxy billions of years ago. And we're collecting these puzzles, thousands of them, hoping that eventually the pattern will emerge. Closer to home, let's talk about the moon. Specifically, the origin of the moon. We think we know how it formed. About 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The impact was cataclysmic, vaporizing rock, ejecting debris into orbit. That debris coalesced into the moon. This theory explains a lot. It explains why the moon's composition is similar to Earth's mantle. It explains why the moon is so large relative to Earth. It explains the angular momentum of the Earth-Moon system. But there are problems. For one, the moon's composition is too similar to Earth's. If Theia was a separate body, it should have a different isotopic signature, different ratios of elements. But the moon and Earth are nearly identical in their oxygen isotopes, their titanium isotopes. It's as if the moon is made entirely from Earth's mantle, with no contribution from Theia. But if that's the case, where did Theia go? Some propose that Theia was isotopically identical to Earth by coincidence, that it formed in the same region of the solar nebula. But that seems unlikely. Others propose that the impact mixed the material so thoroughly that Theia's signature was erased. But simulations struggle to reproduce that level of mixing. Another problem is the moon's orbit. Initially, it should have been in Earth's equatorial plane, but it's tilted. Something perturbed it, and we're not sure what. These might seem like minor issues, but they're not. The giant impact hypothesis is the leading theory, but it's not perfect. And until we understand the discrepancies, we can't be confident that we've got it right. The moon is right there, 250,000 miles away, and we've sent people to walk on it. But we still don't fully understand how it came to be. That's humbling. Let's discuss dark flow. In the early 2000s, astronomers noticed something strange. Galaxy clusters are moving in a particular direction toward a region of the sky at hundreds of kilometers per second. This motion is on top of the Hubble expansion. It's as if something outside the observable universe is pulling galaxy clusters toward it. This was called dark flow, and it was controversial from the start. Other teams tried to replicate the result and failed. The signal disappeared in more recent data. It might have been a statistical fluke, an artifact of how the data was processed. But for a while, it was tantalizing. If dark flow were real, it would imply structure beyond the cosmic horizon, regions of the universe we can never see, exerting gravitational influence on our local neighborhood. It would mean the observable universe is a small patch in something much larger, and the larger structure has its own dynamics, its own flow. Even if dark flow isn't real, the question remains, is there something beyond the horizon? In principle, the universe could extend infinitely, or it could be finite and closed. We can't see beyond the horizon, so we can't know. We're trapped in a bubble, and we can only infer what lies outside by its effects on what we can see. It's like being in a room with no windows. You can hear sounds from outside, feel vibrations through the walls, sense hints of a larger world. But you can't see it directly. That's our situation in cosmology. We're in a room and we're trying to deduce the shape of the building, the layout of the city, the size of the planet, all from indirect clues. Here's another one, the Eridanus supervoid. It's a region of space about 1 billion light-years across where there are far fewer galaxies than average. Voids are common in the large-scale structure of the universe, but this one is unusually large. And it corresponds to a cold spot in the cosmic microwave background, a region where the temperature is slightly lower than average. The cold spot was detected by the WMAP satellite and confirmed by Planck. It's statistically anomalous, unlikely to occur by chance. Some have proposed that it's caused by the supervoid, that photons lose energy climbing out of the gravitational well of the void, creating a cold spot. But the effect is too small. The void can't fully explain the cold spot. So what's going on? Is it a statistical fluke, a rare fluctuation that we happen to find because we looked hard enough? Is it a sign of new physics, a window, or even a bruise from a collision with another universe in the multiverse? We don't know. The cold spot sits there, in the southern sky, colder and larger than it should be, a blemish on the cosmic microwave background, unexplained and unsettling. Now let me talk about something truly strange, the delayed choice quantum eraser experiment. It's one of the most mind-bending experiments in quantum mechanics, and it shows that the future can affect the past in a sense. Here's how it works. You send photons through a double slit, creating an interference pattern. Then you tag the photons, marking which slit they went through. The interference pattern disappears because you've measured the path. But then, after the photons have already passed through the slits, you erase the witch path information. The interference pattern reappears. So far, so quantum. But here's the twist. You can delay the erasure, perform it after the photon has hit the detector. And even then, the interference pattern reappears retroactively. The photon knows that its witch path information will be erased in the future, and it behaves accordingly in the past. This doesn't allow you to send information backward in time, for subtle reasons involving how you sort the data. But it shows that causality in quantum mechanics is slippery. The future influences the past, or rather, the distinction between past and future breaks down at the quantum level. What does this mean? It means that time is not as fundamental as we think. Events don't have a fixed order. They're tangled, interwoven, retroactively determined by future measurements. Reality is negotiated between past and future, and the present is just where the negotiation happens. This has implications for the nature of time, for free will, for everything. If the future affects the past, then the past isn't fixed. It's probabilistic, contingent on what happens later. History is fluid, constantly rewritten by the future. And that's deeply weird. Let's talk about neutrinos. They're ghostly particles, barely interacting with matter. Trillions pass through your body every second, and you never notice. They're produced in the sun, in supernovae, in nuclear reactors, in the atmosphere. They're everywhere, but they're almost impossible to detect. We've built massive detectors, buried deep underground to shield them from cosmic rays. We fill them with thousands of tons of water or ice, and we wait for a neutrino to interact, producing a flash of light. It happens maybe once a day. Neutrinos are elusive, but here's the thing. Neutrinos have mass. We thought they were massless for decades, but experiments showed they oscillate between different flavors, and that's only possible if they have mass. This was a major discovery, Nobel Prize winning, because it means the standard model of particle physics is incomplete. The standard model assumes massless neutrinos. Reality disagrees, but we don't know how much mass they have. We know it's tiny, less than a millionth the mass of an electron, but we don't know the exact value. And we don't know if there are other types of neutrinos, sterile neutrinos, that don't interact even through the weak force. Some experiments have hinted at sterile neutrinos. Other experiments have ruled them out. The data is contradictory, frustrating. And sterile neutrinos, if they exist, could be dark matter. They could be the missing mass in the universe, hiding in plain sight, or rather, hiding because they're invisible. Neutrinos also violate a symmetry called CP symmetry, which combines charge conjugation and parity. This violation is necessary to explain why the universe has more matter than antimatter. Without it, matter and antimatter would have annihilated in the early universe, leaving only photons. We wouldn't exist. But the amount of CP violation in neutrinos isn't enough to explain the matter-antimatter asymmetry. There must be other sources, other processes that we haven't discovered. Neutrinos are a clue, but they're not the whole answer. And then there's the solar neutrino problem, which was a mystery for decades. The sun produces neutrinos through nuclear fusion, and we can calculate how many should reach Earth. But when we detected them, we found only about a third of the expected number. Were our models of the sun wrong? Were the detectors malfunctioning? The answer turned out to be neutrino oscillation. Electron neutrinos produced in the sun convert to muon and tau neutrinos on the way to Earth, and the early detectors could only see electron neutrinos. Once we built detectors sensitive to all flavors, the numbers matched. The sun was fine. Neutrinos were just more interesting than we thought. This is a victory for science, a mystery solved. But it's also a reminder that even our sun, the star we study most closely, can surprise us. Let me tell you about the Great Attractor. It's a gravitational anomaly, a region of space toward which our galaxy and millions of others are being pulled. It's hidden behind the zone of avoidance, a region of the sky obscured by the dust and gas of our own galaxy. We can't see it directly. We can only infer its existence from the motion of galaxies. The Great Attractor is enormous, with the mass of tens of thousands of galaxies. Is pulling us toward it at 600 kilometers per second. But it's not the end of the story. Beyond the Great Attractor is an even larger structure, the Shapley supercluster, a concentration of mass so vast that it influences the motion of galaxy superclusters across hundreds of millions of light-years. We're caught in a cosmic flow, drifting toward concentrations of mass we can barely see. It's humbling. We like to think of space as empty, but it's full of structure, full of gravity wells and filaments and voids. We're floating in a web and we're not in control. The large-scale structure of the universe looks like a sponge or a neural network. Galaxies cluster into filaments, separated by voids. The filaments intersect at nodes, galaxy superclusters, the largest gravitationally bound structures in the universe. And the whole thing is expanding, driven by dark energy, stretching the web tighter. If you could see the universe from outside, you'd see this pattern, this cosmic web, and it's beautiful. It's the result of gravity amplifying tiny quantum fluctuations in the early universe, turning them into the galaxies and clusters we see today. Structure emerged from chaos, order from randomness, through the simple action of gravity over billions of years. But there's a puzzle. The universe is too structured. Simulations of structure formation, based on dark matter and dark energy, predict a certain amount of clustering. But observations show more clustering than expected. The universe has lumpier than it should be. This is called the sigma-8 tension, and it's one of several tensions in cosmology right now. Different measurements of the same quantities give different answers. The Hubble constant, the rate of expansion, differs depending on how you measure it. The amount of matter in the universe differs. The amplitude of fluctuations differs. These might be measurement errors. They might be systematic effects we haven't accounted for. Or they might be signs of new physics, cracks in the standard model of cosmology. We won't know until we get more data, better data, and that takes time and money and effort. But the tensions are exciting because they suggest we're on the verge of something. A new discovery, a new understanding, a paradigm shift, or maybe just a better model. Either way, cosmology is entering a new phase where precision measurements are revealing discrepancies, and discrepancies are where breakthroughs hide. Now let's talk about vacuum decay again, because it deserves more attention. The idea is that the vacuum we live in, the lowest energy state of empty space, might not be the true vacuum. It might be a false vacuum, a metastable state that could decay to a lower energy state. If this happens, a bubble of true vacuum nucleates somewhere, expanding at the speed of light. Inside the bubble, the Higgs field has a different value. Particles have different masses. The electromagnetic force has a different strength. Chemistry doesn't work the same way. Atoms can't form. Everything is destroyed and replaced by a new kind of matter, governed by new laws. This is called vacuum decay or vacuum metastability, and it's not just theoretical. The shape of the Higgs potential, measured at the Large Hadron Collider, suggests that we might be in a metastable state. The vacuum might be on the edge of stability. The good news is, even if we're metastable, the decay rate is incredibly low. The probability of a bubble nucleating in any given region of space, in any given second, is vanishingly small. We're safe for trillions upon trillions of years, far longer than the current age of the universe. But here's the catch. Quantum tunneling isn't the only way to trigger vacuum decay. High-energy processes like those in the early universe or near black holes could push the Higgs field over the barrier. And if vacuum decay has happened elsewhere in the universe, the bubble walls are expanding at light speed. One could reach us at any moment. There's no way to detect it, no way to prepare, no way to survive. The bubble wall would hit us, and we'd cease to exist, replaced by a new vacuum with new physics. It's the ultimate existential threat, unavoidable, unpredictable, and absolute. Does this keep me up at night? Not really. The probability is so low that worrying about it is irrational. But it's a reminder that the universe is not a safe place. It's a place where laws can change, where stability is temporary, where everything we know could be erased in an instant by processes we barely understand. And yet, here we are. The vacuum hasn't decayed yet. We're still here, contemplating these possibilities, marveling at the universe's complexity and danger. That counts for something. Let me end with the biggest mystery of all: consciousness. What is it? How does it arise? Why does anything have subjective experience? This is called the hard problem of consciousness, and it's genuinely hard. We have no idea how to bridge the gap between physical processes and subjective experience. You can explain how neurons fire, how signals propagate, how the brain processes information. You can map the neural correlates of consciousness, the brain regions that light up when you're aware. But none of that explains why there's something it's like to be you, why the lights are on, why you experience redness when you see red, instead of just processing wavelengths of light. Some argue that consciousness is an illusion, that there's no hard problem because there's nothing to explain. But that doesn't work. The one thing you can't doubt is your own experience. Even if everything else is an illusion, the illusion itself is real. There's something it's like to be fooled. Others argue that consciousness is fundamental, that it's a basic feature of the universe like space or time or mass. This is panpsychism, and it's gaining traction among philosophers and some physicists. If consciousness is fundamental, then the hard problem dissolves. You don't have to explain how it emerges because it doesn't emerge. It's always there, woven into the fabric of reality. But that raises new questions. If consciousness is fundamental, then everything is conscious, at least to some degree. Electrons are conscious. Photons are conscious. Rocks are conscious. This seems absurd, but maybe our intuitions are wrong. Maybe consciousness comes in degrees, and human consciousness is just a particularly complex form. Integrated information theory tries to quantify this. It says consciousness is a measure of how integrated and differentiated a system is. A brain has high integrated information because its parts work together in complex ways. A collection of isolated neurons has low integrated information. A rock has even less. But this leads to strange conclusions. According to integrated information theory, certain networks, even non-biological ones, could be conscious if they have enough integrated information. A grid of logic gates arranged the right way could be conscious. A sufficiently complex computer program could be conscious. And maybe certain physical systems, like some crystal lattices, have low but non-zero consciousness. This sounds like science fiction, but it's serious science. And if it's true, it means consciousness is everywhere in varying degrees, and we're just one point on a spectrum that extends from rocks to gods. Alternatively, consciousness might be quantum. Some argue that the brain exploits quantum effects, that microtubules in neurons are quantum computers, and consciousness arises from quantum coherence and entanglement. This is called orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff. The problem is, the brain is warm and wet, not the kind of environment where quantum effects usually survive. Decoherence happens almost instantly. How could the brain maintain quantum coherence long enough to do anything useful? We don't know. Maybe biology has found a way. Maybe quantum effects are protected in certain structures. Maybe consciousness requires quantum mechanics. Or maybe not. Maybe consciousness is purely classical, emerging from the complexity of neural networks. Maybe it's a matter of organization, not substrate. Maybe any system with the right kind of feedback loops and information processing will become conscious, regardless of whether it's made of neurons or silicon. We don't know. And that's the point. Consciousness is the last great frontier. We've split the atom, mapped the genome, photographed black holes. But we still don't understand what it's like to be anything. And here's the final twist. If we don't understand consciousness, then we don't fully understand ourselves. We're mysteries to ourselves, and that's both humbling and exhilarating. It means there's still so much to discover, not just out there in the cosmos, but in here, in the 3 pounds of tissue between your ears. You are the universe becoming aware of itself. You are stardust contemplating stars. And you are fundamentally inexplicable, at least for now. So here's where we are. We live in a universe we don't understand. We're made of particles whose properties we can barely explain. We're conscious and we don't know why. We're alone or we're not, and we don't know which is true. We're searching for answers, and every answer leads to more questions. But that's okay. That's the process. That's science. It's not about certainty. It's about curiosity. It's about looking at the darkness and saying, I wonder what's out there, and then building a telescope to find out. The paradoxes that keep scientists awake at night are the same paradoxes that should keep all of us awake. Not with fear, but with wonder, because these aren't just abstract problems. They're questions about the nature of reality, about who we are, about where we came from and where we're going. And we're privileged to live in a time when we can ask these questions and have a reasonable hope of answering some of them. Not all, maybe not even most, but some. And that's enough. The universe is vast and strange and beautiful and terrifying. It doesn't care about us. It doesn't owe us anything, but it gave us minds capable of understanding it, at least in part. And that's a gift beyond measure. So keep asking, keep wondering, keep probing the boundaries of the known. Because out there, in the darkness, in the silence, in the quantum foam and the cosmic web and the singularities and the horizons, there are answers. And maybe, just maybe, we'll find them. Or maybe we won't. Maybe some questions are unanswerable. Maybe the universe is under no obligation to make sense to us. Maybe we're limited, finite, doomed to see only shadows on the wall of Plato's cave, forever cut off from the full truth. But even so, we'll keep trying, because that's what we do. That's what it means to be human. We reach for the stars, even knowing we might never grasp them. We ask why, even when there's no answer. We build, explore, discover, create meaning in a cosmos that started without it. And that's not futile. That's beautiful. These cosmic paradoxes, these impossible questions, they're not obstacles. They're invitations. The universe is saying, come, explore, wonder. There's more here than you ever imagined. And we're responding. With telescopes and particle accelerators and mathematical theorems and late nights staring at equations that don't quite work. We're pushing back the darkness, one photon at a time, one calculation at a time, one insight at a time. Will we solve all the paradoxes? Probably not, but we'll solve some. And in solving them, we'll uncover new ones, deeper and stranger than before. The frontier of knowledge never stops expanding. There's always another layer, another mystery, another question, and that's perfect, because a universe without mysteries would be a universe without discovery. And a universe without discovery would be a universe without wonder. And a universe without wonder would be unbearable. So embrace the paradoxes. Let them confound you, challenge you, inspire you. Let them remind you that reality is richer than any story we tell about it. Let them keep you humble, keep you curious, keep you searching. Because the universe is waiting. It has secrets to share. If we're brave enough to look, smart enough to listen, patient enough to learn. The night sky is full of questions. And somewhere in the darkness between the stars are the answers. We just have to find them. Let me tell you about the faint young sun paradox. For billion years ago, the sun was only about 70% as bright as it is today. Stars get brighter as they age, fusing hydrogen into helium, increasing their core density and temperature. So the early Earth should have been frozen solid, a snowball world where life could never have started. But it wasn't. We have geological evidence of liquid water on Earth's surface going back almost 4 billion years. We have fossils of microbial life from 3.5 billion years ago. The Earth was warm enough for life, even though the sun was dim. How? The answer might be greenhouse gases. Early Earth had a thicker atmosphere, rich in carbon dioxide and methane, trapping heat and keeping the planet warm. But the numbers don't quite work. You need implausibly high concentrations of greenhouse gases to compensate for the dim sun. And there's evidence that carbon dioxide levels weren't that high. Maybe clouds played a role. Fewer clouds mean less reflection of sunlight, more warming. Maybe the Earth's rotation was faster, creating different atmospheric circulation patterns. Maybe there were periods of freezing, and life survived in refugia, pockets of warmth near volcanic vents or impact craters. Or maybe our understanding of stellar evolution is wrong. Maybe the sun was brighter in the past than we think, or maybe it varied more than we expect. But that seems unlikely. We understand stellar physics pretty well, and the sun is a standard main sequence star. The faint young sun paradox remains unsolved. It's a reminder that even Earth's history, our own planet's story, contains mysteries. We don't fully understand how we got here, how life survived, how the conditions for our existence were maintained for billions of years. Now let's talk about gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. They release more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. They're so bright that we can see them from across the observable universe. There are two types. Short gamma-ray bursts last less than 2 seconds and are caused by colliding neutron stars or a neutron star merging with a black hole. Long gamma-ray bursts last more than 2 seconds and are caused by collapsing massive stars, hypernovae that form black holes. When a gamma-ray burst goes off, it releases a collimated jet of radiation, a beam of gamma rays traveling at nearly the speed of light. If that beam is pointed at Earth, we see a gamma-ray burst. If it's pointed elsewhere, we miss it, which means for every burst we see, there are hundreds we don't. The energy involved is staggering. A typical long gamma-ray burst releases about 10 to 44 joules in a few seconds. That's 100 times more energy than the sun will emit in its entire lifetime, compressed into seconds. If a gamma-ray burst went off in our galaxy, pointed at Earth, it would be catastrophic. The gamma rays would strip away the ozone layer, exposing the surface to lethal ultraviolet radiation. Mass extinction would follow. In fact, some paleontologists think a gamma-ray burst might have caused the Ordovician extinction about 450 million years ago, when 60% of marine species died. There's no direct evidence, but the timing is suggestive, and gamma-ray bursts are common enough that Earth should be hit by one every few 100 million years. But here's what puzzles me. Gamma-ray bursts are so powerful, so concentrated, that they seem to violate energy conservation. Where does all that energy come from? The collapsing star has gravitational potential energy, rotational energy, magnetic energy. But when you add it all up, it's not enough. You need an efficiency close to 100%, converting mass directly into gamma rays. That's hard to do. The leading model involves black hole accretion. The collapsing core forms a black hole surrounded by a disk of infalling matter. The disk is incredibly hot, incredibly dense, and magnetic fields channel energy into jets that punch through the star and blast into space. This can explain the energy, but the details are murky. We can't simulate it accurately because the physics is too complex, involving general relativity, magnetohydrodynamics, nuclear reactions all at once. And then there's the mystery of ultra-long gamma-ray bursts, which last tens of minutes to hours. What could sustain such a long burst? A massive star collapsing doesn't take that long. Maybe it's a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, spinning down and releasing energy. Maybe it's a tidal disruption event, a star being torn apart by a supermassive black hole. We're not sure. Every gamma-ray burst is different. Some have afterglows that last for weeks, fading slowly as the jet interacts with surrounding material. Others fade in hours. Some produce gravitational waves, detected by LIGO when neutron stars collide. Others don't. The diversity suggests multiple mechanisms, multiple pathways to the same explosive endpoint. And we're seeing them from the early universe, from when the cosmos was young and stars were just forming. Gamma ray bursts are beacons, illuminating the distant past, showing us what the universe looked like billions of years ago. They're also laboratories, places where physics operates under extreme conditions we can never reproduce on Earth. Let me take you to the edge of a black hole. Not the event horizon, but closer. The ergosphere. It's a region outside the horizon where space-time itself is dragged along by the black hole's rotation. If you were in the ergosphere, you couldn't stand still, no matter how hard you tried. Space itself is moving, and you're carried with it. This is called frame dragging, and it's a prediction of general relativity. Every rotating object drags space-time around it, but the effect is tiny unless the object is incredibly massive and spinning incredibly fast. For Earth, the frame dragging is measured in milliarcseconds per year. For a rotating black hole, it's extreme. Roger Penrose realized you could extract energy from the ergosphere. Send a particle into the ergosphere, split it into two parts, throw one part into the black hole, and the other part escapes with more energy than the original particle had. You've extracted energy from the black hole's rotation. This is called the Penrose process, and it's real. In principle, you could power a civilization by dropping matter into a rotating black hole and harvesting the energy. But there's a limit. As you extract energy, the black hole spins down. Eventually, it stops rotating, and the ergosphere disappears. A black hole can lose up to 29% of its mass through the Penrose process before it stops spinning. That's an enormous amount of energy, equivalent to converting mass to energy with 29% efficiency. Far better than nuclear fusion. Some think this might explain quasars, the brightest objects in the universe. Quasars are supermassive black holes at the centers of galaxies, accreting matter at prodigious rates. They shine so brightly that they outshine their entire host galaxies. Maybe the energy comes not just from accretion, but from extracting the black hole's rotational energy. But there's a problem. The Penrose process requires very specific conditions, and it's not clear if nature can achieve them. Most models of quasar energy generation rely on accretion alone, with magnetic fields channeling the energy into jets. The Penrose process might be a sideshow, or it might not happen at all. Still, the idea is tantalizing. Black holes aren't just destructive, they're potentially useful. If you could control a black hole, you could power an interstellar civilization for billions of years. You could even use it as a gravitational slingshot, accelerating spacecraft to relativistic speeds without expending fuel. Black holes could be the power plants and highways of the far future. Of course, there's the small problem of not falling in. Here's another cosmic mystery: the Sunyaev-Zel'dovich effect. When photons from the cosmic microwave background pass through galaxy clusters, they interact with hot electrons in the intracluster gas. The electrons give energy to the photons, shifting them to higher frequencies. This creates a distinctive signature, a distortion in the cosmic microwave background. We use this to detect galaxy clusters, even ones too distant to see directly. The Sunyaev-Zel'dovich effect gives us a way to map the distribution of matter in the universe, independent of distance. But there's a puzzle. The effect is stronger than expected. The gas is hotter, denser, than our models predict. Why? Maybe galaxy clusters are more turbulent than we thought. Maybe there's energy input from supermassive black holes, from supernovae, stirring the gas and heating it. Maybe our models of cluster formation are incomplete. Or maybe it's telling us something about dark matter, about how it interacts with ordinary matter. This isn't a crisis, but it's a tension. The universe is slightly different from what we predicted, and understanding why matters. Every discrepancy is a clue, And if we follow enough clues, we might uncover something fundamental. Let's discuss antimatter. For every particle, there's an antiparticle. Antielectrons, antiprotons, antineutrinos. When matter and antimatter meet, they annihilate, converting mass into pure energy. This is the most efficient energy source possible, with 100% conversion of mass to energy. The Standard Model predicts that the Big Bang should have created equal amounts of matter and antimatter. But if that's true, they should have annihilated each other, leaving only photons. The universe should be empty, yet here we are. There's matter, lots of it, and very little antimatter. This is called the baryon asymmetry problem, and it's one of the deepest mysteries in cosmology. Something violated the symmetry between matter and antimatter. Somewhere in the first microseconds after the Big Bang, processes occurred that favored matter over antimatter, creating a tiny excess, one extra matter particle for every billion matter-antimatter pairs. That tiny excess is everything. It's us. It's the stars, the planets, the galaxies. The rest annihilated, and the leftover matter became the universe we see. But what caused the asymmetry? We know of processes that violate charge parity symmetry, creating a preference for matter. Quarks decay slightly differently from antiquarks. Neutrinos oscillate differently from antineutrinos. But the amount of CP violation we've observed isn't enough to explain the baryon asymmetry. Not even close. There must be other sources, other processes, operating at higher energies than we've probed. Maybe grand unified theories, which merge the electromagnetic, weak, and strong forces at extremely high energies. Maybe leptogenesis, where heavy neutrinos decay asymmetrically, creating an excess of leptons that later converts to baryons. Maybe something involving the Higgs field or inflation or physics beyond the Standard Model. We don't know, and it's frustrating because the answer is baked into the universe. It happened. We're the proof. We just don't know how. Some have proposed that there are antimatter galaxies, regions of the universe made entirely of antimatter, separated from matter regions by vast voids. If matter and antimatter never meet, there's no annihilation, no problem. But we don't see evidence for this. Annihilation at the boundaries between matter and antimatter regions would produce a characteristic gamma-ray signature, and we don't see it. The universe seems to be made almost entirely of matter. Almost. We do find antimatter created in high-energy processes, cosmic rays, supernovae, particle collisions in accelerators. But it's always produced alongside matter, and it doesn't last long. It annihilates with the surrounding matter in microseconds. Antimatter is ephemeral, a ghost of symmetry past. Unless we make it ourselves, we can produce antiprotons, positrons, even antihydrogen atoms in particle accelerators. We've trapped antimatter, studied its properties, confirmed that it behaves exactly like matter except for its charge. Antimatter falls down in gravity, not up. It has the same mass, the same quantum numbers. It's not exotic. It's normal, just rare. But storing antimatter is hard. It annihilates on contact with matter, so you have to levitate it with magnetic or electric fields. You have to keep it in a perfect vacuum, isolated from walls, air, dust. The longest we've kept antimatter trapped is about a year, and that was a handful of antiprotons. Making enough antimatter to power a spacecraft, as in science fiction, would require energy inputs far beyond anything we can imagine. It's theoretically possible, but practically absurd. Still, antimatter exists, and it's a window into the early universe. If we could understand why matter won, we'd understand a crucial chapter in cosmic history. We'd know why we exist. Here's a thought experiment that's become a real experiment: the quantum delayed choice entanglement swap. It takes the weirdness of quantum mechanics and amplifies it. You entangle two pairs of particles, A and B, C and D. Then you perform a measurement on B and C, entangling them. This retroactively creates entanglement between A and D, even though they never interacted. Now delay the measurement on B and C until after measurements on A and D have been made. The results for A and D show correlations that shouldn't exist because they weren't entangled when measured. But they become retroactively entangled after the fact. This has been done in labs. It works, and it's profoundly strange. It means that quantum correlations can be created after the fact, that the order of events doesn't matter in the way we classically think it does. Causality is negotiable in quantum mechanics. What does this mean for the nature of time? For the nature of reality? If the past can be changed by future measurements, then the past isn't fixed. It's contingent, probabilistic, waiting to be determined by what we do later. Reality is a tapestry woven from both ends, past and future braided together, and the present is just where they meet. This isn't metaphysics. This is physics, and it suggests that our intuitions about time, causality, reality are wrong. We live in a universe far stranger than common sense allows. Let me tell you about cosmic inflation in more detail. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion. Space doubled in size, then doubled again and again and again 60 times in 10 to 32 seconds. A region smaller than an atom expanded to the size of a grapefruit, then to the size of a galaxy, then to something incomprehensibly large. Inflation explains why the universe is so flat, so uniform, why the cosmic microwave background has the same temperature in all directions. It explains the large-scale structure, the distribution of galaxies. Tiny quantum fluctuations, stretched to cosmic scales by inflation, became the seeds of structure, the slight overdensities that gravity amplified into galaxies and clusters. But inflation creates problems. What drove it? A field called the inflaton, but what is that field? Where did it come from? Why did it start inflating? Why did it stop? We have models, dozens of them, but no definitive answer. And inflation might be eternal. Once it starts, quantum fluctuations ensure it never fully stops. Inflation continues in some regions, while in others it stops and normal expansion takes over, creating pocket universes. Our observable universe is one such pocket, but there are infinitely many others, each with its own properties, its own laws. This is the multiverse again. And if inflation is eternal, the multiverse is not just large, it's infinite. Anything that can happen does happen somewhere. Every possible universe exists. You exist in infinitely many versions with infinitely many variations. There are universes where you made different choices, where history unfolded differently, where the constants of nature are different. Some find this idea liberating. Others find it horrifying. If everything happens, then nothing is special. Your choices don't matter because all choices are made in some universe. Morality becomes arbitrary. Meaning dissolves. But maybe that's wrong. Maybe meaning is local. It matters here, in this universe, even if it doesn't matter cosmically. Your choices affect this world, this timeline, this branch of reality. That's enough. Or maybe the multiverse doesn't exist. Maybe inflation isn't eternal. Maybe there's only one universe, ours, and the appearance of fine-tuning is a cosmic coincidence, or the result of a deeper theory that picks out this universe uniquely. We don't know. What we do know is that inflation explains the data better than any alternative. It predicts the pattern of fluctuations in the cosmic microwave background with stunning accuracy. It's the best theory we have, but it's incomplete, and it raises as many questions as it answers. Let's talk about magnetic fields. They're everywhere. Earth has one, the sun has one, galaxies have them, galaxy clusters have them. Even the intergalactic medium has weak magnetic fields. But where do they come from? For Earth, it's the dynamo effect. Convection in the liquid iron core generates electric currents, which create magnetic fields, which twist and amplify through feedback. It's a self-sustaining process, powered by heat from radioactive decay and leftover heat from Earth's formation. But for galaxies, it's more complicated. Galaxies have coherent magnetic fields, aligned along spiral arms, with strengths around a few microgauss. That doesn't sound like much, but spread over tens of thousands of light years, it's a huge amount of magnetic flux. How did it get there? The leading theory is the galactic dynamo. Stars, supernovae, and turbulent gas motions twist and amplify weak seed fields. Over billions of years, this builds up to the observed field strengths. But it requires seed fields to start with, and we don't know where those come from. Maybe they were created in the early universe shortly after the Big Bang. Maybe they're relics of phase transitions or cosmic inflation. Maybe they were generated by the first stars, by battery processes where charged particles separate in ionized plasma. All of these mechanisms could contribute, but none fully explains the observations. And then there are magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. These fields are so intense that they warp the vacuum, affecting the orbits of electrons, distorting atoms. If you were within 1,000 kilometers of a magnetar, its magnetic field would kill you by disrupting the molecular bonds in your body. How do magnetars get such strong fields? Maybe they're born that way, forming when a massive star with a strong field collapses. The field lines are compressed, amplifying the field. Or maybe dynamo processes in the newborn neutron star, powered by rapid rotation, amplify the field. We've observed magnetars spinning down, releasing energy through magnetic braking. Some produce giant flares, eruptions that briefly outshine entire galaxies in gamma rays. One such flare, from SGR 1806 to 20 in 2004, was the brightest event ever observed from outside the solar system. In a tenth of a second, it released more energy than the sun emits in 150,000 years. If it had been within 10 light years of Earth, it would have caused a mass extinction. Magnetars are extreme, violent, and beautiful. They're laboratories for physics we can't replicate anywhere else. And they're reminders that the universe is capable of things we can barely imagine. Here's something that sounds like fantasy but is mathematical reality. Closed time-like curves in general relativity. These are paths through space-time that loop back on themselves, allowing travel to the past. Einstein's equations permit them under certain conditions. Rotating black holes, traversable wormholes, infinitely long rotating cylinders, cosmic strings under tension. None of these configurations exist naturally as far as we know. And even if they did, actually using them for time travel requires exotic matter, matter with negative energy density, which violates all known energy conditions. So time travel to the past is probably impossible, but probably isn't definitely. And the fact that general relativity allows it, even in principle, is disturbing. It means our best theory of space-time doesn't prohibit time travel. It suggests that causality is a feature of specific space-time configurations, not a fundamental law. Stephen Hawking proposed a chronology protection conjecture. The laws of physics conspire to prevent time travel, even when general relativity seems to allow it. Quantum effects, vacuum fluctuations, should blow up to infinite density whenever a closed time-like curve tries to form, preventing the formation of time machines. But this is speculative. We don't have a full theory of quantum gravity to test it. Maybe time travel is possible. Maybe the universe is filled with closed time-like curves, and causality is an illusion, a local approximation that breaks down on cosmic scales. Or maybe time has a structure we don't understand, something deeper than the timeline of relativity or the parameter of quantum mechanics. Maybe time is emergent from something more fundamental, and the possibility of time travel is an artifact of treating time as fundamental when it's not. We don't know, and every time we think we've understood time, it slips away, revealing deeper layers of mystery. Let's discuss the cosmic neutrino background. We've detected the cosmic microwave background, photons from 380,000 years after the Big Bang. But there should also be a cosmic neutrino background, neutrinos from 1 second after the Big Bang, when the universe was a hot, dense plasma. These neutrinos have been traveling through space for nearly 14 billion years. They've cooled to a fraction of a degree above absolute zero. They're everywhere, about 300 per cubic centimeter, passing through you, through the Earth, through everything. But we've never detected them. Why? Because they're too low energy. The cosmic neutrino background neutrinos have energies around 10 to 4 electron volts, far below the threshold of any detector we've built. Detecting them would require a detector the size of a planet or a revolutionary new technology. But they're out there, and they carry information about the first second of the universe, a time when the cosmos was too hot and dense for photons to travel freely. The cosmic neutrino background is a snapshot of the universe at 1 second old, a window into an era we can't observe any other way. If we could detect it, we'd learn about the number of neutrino species, the total neutrino mass, the conditions in the early universe. We might even see imprints of physics beyond the standard model, new particles or interactions that existed in the first moments. It's one of the great challenges of experimental physics. How do you detect something that barely interacts at energies too low to measure? The answer might involve quantum sensors, superconducting detectors cooled to microkelvin temperatures, or techniques we haven't invented yet. But someone will figure it out. Eventually, we'll detect the cosmic neutrino background. And when we do, it'll be another triumph, another window opened, another piece of the cosmic puzzle. Let me tell you about quasars. They're the brightest, most distant objects we can see, powered by supermassive black holes at the centers of galaxies. Some quasars are so luminous that they outshine 1 trillion suns. They're visible across billions of light years. But here's the puzzle. Quasars existed when the universe was young, less than 1 billion years old. Supermassive black holes with millions or billions of solar masses were already in place. How? Black holes form from collapsing stars, which have masses of tens of suns. Even if a black hole ate constantly, it would take billions of years to reach supermassive sizes. But the universe wasn't billions of years old yet. Did black holes form differently in the early universe? Maybe there were direct collapse black holes, regions of gas that collapse straight to black holes without forming stars first. Maybe primordial black holes, formed in the first moments after the Big Bang, acted as seeds. Maybe black holes merged rapidly, building up mass faster than we thought possible. We don't know. Every model has problems. Direct collapse requires very specific conditions. Primordial black holes are hypothetical. Mergers are too slow to explain the largest early quasars. And quasars are diverse. Some are radioloud, blasting jets of particles at near light speed. Others are radio quiet. Some are obscured by dust. Others are naked, visible in optical and UV. Some vary on timescales of days, implying that the emission region is light days across. Others are steady. We've learned a lot about quasars, but they still surprise us. We're finding quasars at higher and higher redshifts from earlier and earlier epochs. Each one raises the question, how did you get so massive so fast? And quasars had a profound effect on cosmic history. Their radiation ionized gas in the early universe, clearing out neutral hydrogen, creating bubbles of ionized plasma that eventually merged. This is called reionization, and it transformed the universe from opaque to transparent. Quasars were beacons, lighthouses illuminating the cosmic dark ages. But reionization itself is a mystery. When did it happen? How long did it take? Was it driven by quasars, or by stars, or by both? Observations suggest it was patchy, inhomogeneous, with some regions ionized earlier than others. The cosmic microwave background shows the imprint of reionization, but the details are unclear. We're building new telescopes like the James Webb Space Telescope to study the epoch of reionization in detail. We want to see the first galaxies, the first quasars, the first stars. We want to watch the universe wake up, transitioning from darkness to light. And we're close. The data is coming in. The picture is getting clearer. But as always, every answer raises new questions. Here's one that bothers me, the Hubble tension. The Hubble constant describes how fast the universe is expanding. We can measure it in two ways. Locally, using distances to nearby galaxies and their recession speeds, and cosmologically, using the cosmic microwave background and our model of the universe's history. These two methods give different answers. The local measurement says the universe is expanding at about 73 kilometers per second per megaparsec. The cosmological measurement says 67. That's a 9% difference, and it's statistically significant. It's not going away. Is it a problem with one of the measurements? Are there systematic errors we haven't accounted for? Or is it telling us something fundamental, that our model of the universe is wrong? Maybe dark energy is more complicated than we thought, evolving over time instead of being constant. Maybe there's new physics in the early universe, altering the expansion history. Maybe gravity behaves differently on cosmological scales. Or maybe it's something simpler, an error in how we measure distances. The Hubble tension is unresolved, and it's causing sleepless nights for cosmologists. Because if it's real, if our model is wrong, then we don't understand the universe as well as we thought. And that's exciting because it means there's room for discovery. But it's also frustrating because we've spent decades building a standard model that works beautifully, explaining everything from the Big Bang to the formation of galaxies. And now there's a crack, and we don't know if it's a fatal flaw or a minor issue. Time will tell. More data, better measurements will either resolve the tension or confirm it. And if it's confirmed, cosmology will enter a new era where we have to rethink our assumptions, explore new models, push beyond the standard paradigm. That's how science works. Anomalies drive progress. Contradictions point the way forward. And the Hubble tension might be the most important contradiction in cosmology today. Let me tell you about gravitational waves in more detail. When massive objects accelerate, they create ripples in space-time, waves that propagate at the speed of light. Einstein predicted them in 1916, but we didn't detect them until 2015, when LIGO observed two black holes colliding. That detection was a triumph, a confirmation of general relativity in a regime we'd never tested before. It opened a new window on the universe. We're now detecting gravitational waves regularly. Black hole mergers, neutron star collisions, maybe even exotic events we haven't identified. But gravitational waves are weak. The LIGO detectors are sensitive enough to measure distortions in spacetime smaller than 1,000th the width of a proton. It's an engineering marvel, using lasers, mirrors, and kilometers-long vacuum tubes to detect ripples from collisions billions of light years away. And what we're finding is surprising. Black holes are more common than we thought, and they merge more often. The masses are strange, some much heavier than expected, others in ranges that shouldn't exist according to stellar evolution models. We're seeing systems that challenge our understanding of how stars die, how black holes form, how they pair up and merge. Neutron star collisions are even more interesting. When two neutron stars merge, they produce gravitational waves, gamma-ray bursts, and optical transients called kilonovae. We've observed this once in 2017, and it was spectacular. We detected the gravitational waves first, then the gamma rays seconds later, then optical and infrared emission from the expanding debris. The kilonova was bright, visible for weeks, and spectroscopy revealed signatures of heavy elements: gold, platinum, uranium. These elements are forged in neutron star mergers, in the intense conditions when matter is compressed to nuclear density and then explodes outward. Every gold atom in your jewelry was created in a neutron star collision, somewhere, sometime in the history of the universe. That's profound. You're wearing stardust not just from ordinary stars, but from the most violent collisions in the cosmos. The universe had to destroy stars to create the elements that make up your world. Gravitational waves also travel unimpeded through the universe. Unlike light, they're not absorbed, scattered, or blocked. They carry information from regions we can't see electromagnetically. We can use them to probe the interiors of neutron stars, to test general relativity in extreme conditions, to search for exotic objects like cosmic strings or primordial black holes. And we're just getting started. Future detectors, space-based ones like LISA, will be sensitive to lower-frequency gravitational waves from supermassive black hole mergers, from the early universe, maybe even from cosmic inflation itself. We might detect a stochastic background of gravitational waves, a hum from countless unresolved sources, revealing the gravitational history of the cosmos. Gravitational wave astronomy is in its infancy. A century from now, it'll be routine, and who knows what we'll discover. Here's a paradox that doesn't get enough attention: the black hole entropy problem. Entropy is a measure of disorder, of how many ways you can arrange a system's components. For ordinary matter, entropy scales with volume. A bigger box of gas has more entropy. But for black holes, entropy scales with area, specifically the area of the event horizon. This is the Bekenstein-Hawking entropy formula, and it's weird. Why should entropy depend on surface area instead of volume? The answer might lie in the holographic principle. If information is encoded on the horizon, then the entropy naturally scales with area. The black hole's interior doesn't add to the entropy because the information is all on the surface. But this raises questions. What about the interior? If information is on the horizon, what's inside? Some argue the interior doesn't exist, that it's an illusion, a trick of perspective. What we think is the inside of a black hole is actually encoded on the outside. This sounds absurd, but string theory supports it. In ADS/CFT, a black hole in a higher dimensional space is equivalent to a quantum state on the boundary of that space. The interior emerges from correlations in the boundary theory. Space itself is holographic. If this is true universally, then our three-dimensional space might be a hologram. Everything we see, every depth, every dimension, is encoded on a two-dimensional surface at the edge of the universe. We're shadows cast by information living in fewer dimensions. This is the holographic principle, and it's one of the strangest ideas in modern physics. It suggests that dimensionality is negotiable, that space is emergent, that reality has layers we haven't begun to understand. And it connects to entropy in deep ways. The maximum entropy of any region of space is proportional to its surface area, not its volume. This is the Beakenstein bound, and it constrains how much information can be packed into a region. If you exceed the bound, the region collapses into a black hole. This has implications for computation, for information theory, for the ultimate limits of knowledge. You can't know everything about a region of space because there's a maximum amount of information that can exist there. The universe has built-in limits, boundaries beyond which knowledge becomes impossible. And that's humbling. We're exploring a universe that might be fundamentally incompressible, irreducible, where some questions can never be answered not because we're not smart enough, but because the answers don't exist. Let me end this with a thought about our place in all of this. We're insignificant, cosmically speaking, tiny specks on a tiny world, orbiting an average star, in a galaxy that's one of hundreds of billions. The universe doesn't need us. It got along fine for 13.8 billion years before we appeared, and it'll continue just fine after we're gone. But we're also remarkable. We're the universe's way of knowing itself. Atoms forged in stars, arranged into patterns complex enough to contemplate their own existence. We've figured out where we came from, how old the universe is, what it's made of. We've seen the echoes of the Big Bang. We've detected gravitational waves from colliding black holes. We've walked on the moon. We've done all this in the cosmic equivalent of an eye blink. Civilization is 10,000 years old. Science is 400. And in that time, we've gone from thinking the Earth was flat to mapping the entire observable universe. Imagine what we might accomplish in the next 400 years, the next 4,000. If we survive, if we keep asking questions, keep exploring, keep pushing the boundaries, what might we discover? Maybe we'll solve the paradoxes. Maybe we'll find the theory of everything, uniting quantum mechanics and general relativity. Maybe we'll understand consciousness, time, existence itself. Or maybe we'll find that the universe is deeper than we ever imagined, that every answer reveals infinite questions, that the mystery never ends. Either way, the journey is worth it, because in asking these questions, in confronting these paradoxes, we're doing something extraordinary. We're participating in the universe's self-discovery. We're part of the cosmic story, and that's enough. That's everything. The paradoxes will keep us awake at night. The mysteries will haunt us. The universe will remain strange, beautiful, terrifying, incomprehensible. But we'll keep looking up. We'll keep asking why. And maybe, just maybe, we'll find answers that transform everything we thought we knew. The cosmos is vast. The questions are endless. And we're here, wondering, exploring, reaching for truths that shimmer just beyond our grasp. That's what it means to be human. That's what it means to be alive in this particular corner of space-time, in this brief moment between the Big Bang and heat death, when stars still shine and minds can still wonder. So embrace the paradoxes. Let them drive you forward, because every paradox is an invitation. And the universe is waiting to show you something you've never seen before. Now let me take you deeper into quantum mechanics, to a place where reality itself becomes negotiable. The double-slit experiment. You've probably heard of it, but let me tell you why it should shake you to your core. Send a single electron toward a screen with two slits. Common sense says it goes through one slit or the other, but it doesn't. It goes through both, interfering with itself, creating a pattern on the detector that only makes sense if the electron was in two places at once. Watch which slit it goes through and the pattern changes. The interference disappears. The electron behaves like a particle, not a wave. The act of observation changes what happens. Not because you disturbed it mechanically, but because measurement itself is a physical process that collapses possibilities into actualities. This isn't a metaphor. This is what actually happens. And we've done it with molecules, with large organic compounds containing hundreds of atoms. We've done it with light, with neutrons, with entire systems. The quantum world doesn't care about your intuitions. It follows rules that seem designed to make philosophers weep. But here's what really keeps me up: the implications for reality. Before measurement, the electron isn't secretly in one place that we just don't know about. It's genuinely in a superposition, existing in multiple states simultaneously. The wave function is real, not just a mathematical convenience. And when you measure, something happens. The superposition collapses. But what causes the collapse? What singles out one outcome from many? Nobody knows. And that's after a century of quantum mechanics. We can calculate probabilities with extraordinary precision. We can build technologies that exploit quantum effects. But we can't explain what happens during measurement. It's called the measurement problem, and it's the dirty secret at the heart of physics. Some say there's no collapse. The universe branches and all outcomes occur in parallel universes. Some say consciousness causes collapse. Some say decoherence explains it, that interaction with the environment naturally destroys superpositions. But none of these explanations is fully satisfying. They all have problems, conceptual or mathematical. And this matters because if we don't understand measurement, we don't understand observation. And if we don't understand observation, we don't understand the relationship between reality and knowledge. We don't understand what it means to know something about the world. Let's talk about dark matter candidates more specifically. We know dark matter exists. We see its gravitational effects. But what is it? The leading candidate is WIMPs, weakly interacting massive particles. They'd be heavy, around 10 to 1,000 times the mass of a proton, and they'd interact only through gravity and the weak nuclear force. Dozens of experiments have searched for WIMPs. They use detectors buried deep underground, shielded from cosmic rays, cooled to near absolute zero, waiting for a WIMP to collide with a nucleus. It would happen maybe once a year in a ton of material. And so far, after decades of searching, we've found nothing. Not a single confirmed detection. Maybe WIMPs are lighter than we thought, or heavier, or interact even more weakly. Maybe they're not WIMPs at all. Maybe they're axions, hypothetical particles predicted by solutions to the strong CP problem. Axions would be incredibly light, billions of times lighter than electrons, and they'd interact primarily with photons in strong magnetic fields. We're looking for axions too, using resonant cavities in magnetic fields, searching for the faint photons that would be produced if axions convert to photons. Again, nothing confirmed. The parameter space is vast, and we're searching methodically, but it's like looking for a specific grain of sand on all the beaches of Earth. Or maybe dark matter is primordial black holes, formed in the first moments after the Big Bang. Not from collapsing stars, but from density fluctuations in the early universe. These could have any mass, from microscopic to thousands of solar masses. They'd be invisible, interacting only through gravity, which is exactly what dark matter does. But there are constraints. If dark matter were primordial black holes of certain masses, we'd see effects we don't see. Gravitational lensing of distant stars, disruption of wide binary star systems, effects on the cosmic microwave background. Most mass ranges are ruled out. Only a few windows remain open, and even those are controversial. Maybe dark matter isn't particles at all. Maybe it's a modification of gravity. Mond, modified Newtonian dynamics, proposes that gravity behaves differently at very low accelerations, producing effects that mimic dark matter. It works surprisingly well for galaxy rotation curves, but it fails for galaxy clusters, for the cosmic microwave background, for the large-scale structure of the universe. It's not a complete theory. Or maybe dark matter is something exotic. Mirror matter, hidden sectors, dark photons, sterile neutrinos. The possibilities are endless, constrained only by observations and theoretical consistency. We're feeling around in the dark, literally trying to identify something we can't see by its absence, by the holes it leaves in our understanding. It's frustrating, it's exhilarating, and it's the frontier of particle physics. Somewhere in the data, in the null results and the anomalies, is a clue. We just have to recognize it. Here's a cosmic mystery that touches on the nature of causality. Retrocausality. It's the idea that effects can precede causes, that the future can influence the past. This sounds like science fiction, but certain interpretations of quantum mechanics allow for it. In the transactional interpretation, particles exchange advanced and retarded waves, solutions to the wave equation that propagate forward and backward in time. The transaction, the physical event, is the handshake between these waves. Cause and effect become symmetric, neither fully preceding the other. In the two-state vector formalism, quantum states are described by both a forward-evolving state from the past and a backward-evolving state from the future. The present is determined by both. Your future affects your past, and your past affects your future in a time-symmetric dance. These aren't mainstream views, but they're taken seriously by some physicists because they solve certain problems in quantum mechanics. They eliminate the need for wave function collapse. They explain the EPR paradox naturally. They make sense of the delayed choice experiments, but they require accepting that time doesn't flow the way we think it does, that cause and effect are more flexible than classical intuition allows. And that's a hard pill to swallow, even for physicists who deal with quantum weirdness daily. If retrocausality is real, what does it mean for free will? If your future choices affect your past, are you free? Or are you trapped in a self-consistent loop where the future determines the past, which determines the future? Is time a circle or a line or something else entirely? We don't know. And maybe we can't know because our brains evolved to navigate a world where causes precede effects, where time flows forward, where the past is fixed and the future is open. We're trying to understand physics that violates these assumptions, using minds shaped by those assumptions. We might be fundamentally limited, or maybe we'll adapt. Maybe future humans, augmented by technology or evolution, will think naturally in terms of retrocausality of time-symmetric physics. Maybe they'll look back at us and wonder how we ever managed with such a primitive understanding of time. Let's discuss cosmic voids in more detail. The universe isn't uniform. Galaxies cluster into groups, clusters, superclusters, arranged in filaments and sheets. And between these structures are voids, vast regions containing very few galaxies. The largest known void is the Boötes void, discovered in 1981, about 330 million light-years in diameter. It contains only about 60 galaxies, compared to the 2,000 you'd expect in such a volume. It's not completely empty, but it's remarkably underdense. What created the voids? Gravity. In the early universe, matter was almost uniformly distributed with tiny fluctuations. Gravity amplified these fluctuations. Overdense regions attracted more matter, becoming denser. Underdense regions lost matter, becoming emptier. Over billions of years, this process created the cosmic web, dense filaments surrounding voids. But voids aren't static. They're expanding faster than the average expansion of the universe. Galaxies are streaming away from void centers, piling up on void edges. This creates a peculiar velocity field, a pattern of motion superimposed on the Hubble flow. And voids might tell us about dark energy. The expansion of voids is sensitive to the nature of dark energy, to whether it's constant or evolving. By mapping voids, measuring their sizes and expansion rates, we can constrain models of dark energy. Some have proposed using voids as cosmological laboratories. They're pristine environments, relatively unaffected by the complex astrophysics of galaxies and clusters. Studying voids might reveal subtle effects that are washed out in denser regions. There's even speculation about void-dwelling civilizations. If you wanted to avoid cosmic hazards, supernovae, gamma-ray bursts, radiation from quasars, you'd build your civilization in a void. You'd have clear skies, low backgrounds, perfect isolation. Of course, you'd also have fewer resources, fewer nearby stars to colonize. But maybe that's a worthwhile trade-off. We haven't found any evidence of civilizations in voids, but we haven't looked hard. And if they're there, staying quiet, we might never know. Now let me tell you about the Unruh effect. If you accelerate through empty space, you'll detect thermal radiation, a bath of particles that isn't there for stationary observers. The harder you accelerate, the hotter the radiation. It's called the Unruh effect, and it's a direct consequence of quantum field theory in curved spacetime. For an observer accelerating at the acceleration of Earth's gravity, the Unruh temperature is about 4x 10 to minus 20 Kelvin. That's immeasurably small. But for an observer accelerating at 10 to 20 m/s2, about what you'd experience near the event horizon of a stellar mass black hole, the temperature is about 1 Kelvin. That's measurable, at least in principle. The Unruh effect is deeply connected to Hawking radiation. From the perspective of an accelerating observer, the vacuum is full of particles. From the perspective of a stationary observer, those particles don't exist. Reality depends on your acceleration, on your reference frame. This has profound implications. It means that particles, the basic constituents of matter, are observer-dependent. What's empty space for one observer is a thermal bath for another. The vacuum isn't a fixed thing. It's relative, contingent, dependent on motion. And if particles are observer-dependent, what does that say about reality? Is there an objective universe? Or is everything perspectival, dependent on who's looking and how they're moving? Some physicists argue that this shows particles aren't fundamental. Fields are fundamental. Particles are excitations of fields, and which excitations exist depends on how you slice up the field, which depends on your reference frame. Particles are convenient fictions, patterns we impose on a more fundamental reality. But this is unsettling. We think of particles as real, as things that exist independently of observation. The Unruh effect says that's wrong. Existence itself is frame-dependent, and we've never directly detected the Unruh effect. It's too small for any acceleration we can produce in a lab. But we've detected Hawking radiation's analog in acoustic systems, in fluids, in condensed matter systems. These analog gravity experiments suggest the Unruh effect is real, that the mathematics works. but we'd like to see it directly in actual particles in actual vacuum. Maybe someday. Technology advances, experiments get more precise. Or maybe we'll never see it, and it'll remain a theoretical curiosity, a consequence of quantum field theory that we trust but can't directly confirm. Let's talk about planet formation. We have a decent understanding of how planets form. Gas and dust in a protoplanetary disk collide, stick together, grow. Small grains become pebbles, pebbles become boulders, boulders become planetesimals, planetesimals become planets. Gravity takes over when objects get large enough, accelerating the process. But there are problems. The meter-size barrier. For one, meter-sized objects in a disk experience strong drag from gas. They should spiral into the star in a few hundred years, never growing large enough to become planets. Yet planets exist. We're standing on one. The solution might be streaming instabilities, where pebbles concentrate locally, forming clumps that collapse directly into planetesimals. Or maybe pebble accretion, where planetesimals grow by accreting small pebbles that are coupled to the gas. These mechanisms can bypass the meter-size barrier, allowing rapid growth. But the details are murky. Simulations struggle to reproduce observed planet systems. We find hot Jupiters, massive planets orbiting close to their stars, where they shouldn't be. We find super-Earths, planets larger than Earth but smaller than Neptune, which don't exist in our solar system. We find systems with planets in orbital resonances, synchronized like clockwork, and systems with chaotic orbits, planets on the brink of ejection. The diversity of exoplanet systems is staggering. Every one is different. Some have multiple planets. Some have one. Some have debris disks. Some are bare. The more we discover, the more we realize our solar system isn't typical. It's one outcome among many, maybe even unusual. And there are mysteries within our own solar system. Why is Mars so small? It's in the right location to be a large planet between Earth and Jupiter. But it's tiny, barely a tenth of Earth's mass. Something stunted its growth. Maybe Jupiter's gravity stirred the asteroid belt, preventing planetesimals from accreting into Mars. Maybe Mars lost mass through collisions. We're not sure. Why doesn't Venus have a moon? Earth has one formed from a giant impact. If Venus experienced a similar impact, where's its moon? Maybe it did have a moon and it spiraled in, crashing into Venus. Maybe the impact that formed Venus's moon was different, producing a satellite that didn't survive. Why is Earth's water so abundant? Water is volatile, easily evaporated in the hot inner solar system. Earth should be dry, but it's not. Maybe asteroids brought water. Maybe comets. Maybe water was trapped in minerals, released later by volcanism. Or maybe Earth formed far from the sun and migrated inward, preserving its water. These are questions about our own cosmic backyard, and we're still figuring them out. Here's something strange about pulsars. They're rotating neutron stars, beaming radiation from their magnetic poles. As they spin, the beams sweep across space like lighthouses. If Earth is in the beam's path, we see pulses, regular as clockwork. Some pulsars pulse thousands of times per second, but pulsars slow down. They lose rotational energy, emitted as electromagnetic radiation and particle winds. Eventually, they spin too slowly to emit, and they disappear from view. This is called the pulsar graveyard, and it's full of dead neutron stars, invisible, spinning silently through space. Except some pulsars speed up. They glitch, sudden increases in rotation rate. The interior of the neutron star, A superfluid of neutrons transfers angular momentum to the crust. It's like a cosmic ice skater pulling in their arms, spinning faster. But how does this happen? The interior and crust are coupled, but not perfectly. The superfluid can rotate faster than the crust, storing angular momentum. When the two phases reconnect, angular momentum transfers suddenly, causing a glitch. We've observed thousands of glitches, but we don't fully understand the mechanics. The interior of a neutron star is extreme, with densities higher than atomic nuclei, pressures beyond anything in terrestrial labs. Matter behaves in ways we can't replicate, governed by physics we can't fully compute. Neutron stars might have quark cores, regions where neutrons dissolve into their constituent quarks. They might have pion condensates, strange phases of nuclear matter. They might have crusts made of exotic nuclei, neutron-rich isotopes that don't exist on Earth. Every pulsar is a natural laboratory, testing theories of nuclear physics, of superfluidity, of magnetic fields. And they're giving us data we can't get any other way. There's also the pulsar timing array, a network of pulsars across the sky that we monitor with exquisite precision. Pulsars are such accurate clocks that we can use them to detect gravitational waves. When a gravitational wave passes between Earth and a pulsar, it stretches space, changing the arrival time of pulses. By monitoring many pulsars, we can detect waves that individual detectors can't see. And recently, pulsar timing arrays have found evidence of a gravitational wave background, a stochastic hum from countless sources. Merging supermassive black holes, cosmic strings, maybe the early universe itself. It's a new window, a new way of seeing the cosmos, and we're just beginning to interpret what we're hearing. Let me tell you about rogue planets. Not all planets orbit stars. Some were ejected from their parent systems, flung into interstellar space by gravitational interactions. They wander the galaxy, dark, cold, invisible. We've found a few rogue planets, mostly through microlensing, where a planet passes in front of a background star and briefly magnifies its light. But they're hard to detect. No starlight to reflect, no infrared emission unless they're young and still cooling. They're ghosts. How many rogue planets are there? Estimates vary wildly, from 1 per star to 10 per star. If the upper estimate is right, there are more rogue planets than stars in the galaxy. Hundreds of billions of worlds, drifting alone, never to see a sunrise. Could life exist on rogue planets? Probably not, but maybe. If a planet is massive enough, it could retain heat from its formation, from radioactive decay, from tidal flexing if it has a moon. Subsurface oceans, heated from below, might persist for billions of years. Life, if it arose before ejection, might survive in those oceans, cut off from the cosmos, unaware of stars or galaxies. It's a melancholy thought. Civilizations on rogue planets would have no astronomy, no way to know about the larger universe. They'd think they're alone, adrift in infinite darkness. Would they despair, or would they find meaning in their isolation? We'll probably never know. Rogue planets are too numerous, too distant, too dark to study in detail. They're out there, a hidden population, a reminder that the galaxy is stranger and more diverse than we imagine. Now let's discuss the Planck scale, the smallest meaningful length in physics, about 10 to minus 35 meters. At this scale, quantum fluctuations of spacetime become so intense that the concepts of distance and time break down. Space itself becomes foamy, probabilistic, uncertain. We can't probe the Planck scale directly. It would require energies 10 to 16 times higher than the Large Hadron Collider. We'd need a particle accelerator the size of the galaxy. But we can theorize, and what the theories suggest is radical. At the Planck scale, space-time might be discrete, quantized, made of tiny loops or strings or networks. Loop quantum gravity proposes that space is woven from quantum loops, interconnected like chainmail. String theory proposes that fundamental particles are vibrating strings, and space-time emerges from the interactions of these strings. Both approaches suggest that smooth space-time is an illusion, an approximation that works at large scales but breaks down at small scales. Just as water seems continuous but is made of molecules, space-time seems smooth but might be made of discrete units. If space is quantized, what does that mean? It means there's a smallest possible distance, a pixel size for reality. It means the universe is fundamentally discrete, like a cosmic computer simulation. It means calculus, which assumes continuity, doesn't apply to the deepest level of nature. But we don't know if space is quantized. We have theories, but no experimental evidence. The Planck scale is so far beyond our reach that we might never test these ideas directly. We're forced to rely on indirect methods: cosmology, black holes, thought experiments. And there's the problem of quantum gravity. General relativity describes gravity as curved spacetime. Quantum mechanics describes particles and fields, but they're incompatible. General relativity is deterministic, smooth, geometric. Quantum mechanics is probabilistic, discrete, algebraic. Combining them produces infinities, nonsensical results, mathematical breakdowns. String theory and loop quantum gravity are attempts to solve this, but neither is complete. String theory requires extra dimensions, 10 or 11 total, curled up too small to see. It predicts a vast landscape of possible universes, with no clear way to single out ours. Loop quantum gravity avoids extra dimensions but struggles to reproduce general relativity in the appropriate limit. We've been working on quantum gravity for decades, and we're not close to a solution. It might be the hardest problem in physics, requiring insights we haven't had, mathematics we haven't invented, experiments we can't perform. Or maybe the problem is ill-posed. Maybe gravity isn't quantum. Maybe it's classical and quantum mechanics needs to be modified to accommodate it. Maybe there's a third option, something neither quantum nor classical, that we haven't imagined. We don't know. And that uncertainty, that gap in our understanding, is both humiliating and motivating. We've explained so much from quarks to galaxies, but the deepest question, how to unite our two best theories, remains unanswered. Let's talk about the cosmic web in more detail. If you could see the universe on the largest scales, you'd see a web of filaments, sheets, and nodes with voids in between. Galaxies aren't scattered randomly. They're organized, structured, following paths carved by gravity over billions of years. This structure originated from quantum fluctuations in the early universe, inflated to cosmic scales. Overdense regions attracted matter, underdense regions expelled it. Over time, matter flowed into filaments, the paths of least resistance, creating the web. But the cosmic web isn't static. It's evolving. Filaments are thinning as dark energy pulls the universe apart. Voids are growing. Clusters are merging, forming larger structures. Eventually, in the far future, the web will dissolve. Dark energy will have stretched space so much that galaxies lose contact, and the cosmic web becomes a memory, encoded in the motions of isolated galaxies. We can map the cosmic web using galaxy surveys, measuring the positions and distances of millions of galaxies. The patterns we see match predictions from simulations, confirming our understanding of structure formation. But there are anomalies. The cosmic web has structure on scales larger than expected. There are alignments, correlations that shouldn't exist if the universe is random. Some call this the cosmic axis of evil, though that's an exaggeration. It's more like a hint, a whisper of something we don't understand. Maybe it's a statistical fluke. Maybe it's a sign of new physics, of interactions between our universe and others in a multiverse. Maybe it's telling us about the initial conditions of the Big Bang, about what happened during inflation. We won't know until we have more data, and the cosmic web might contain more than galaxies. There could be gas, ionized plasma filling the filaments. We've detected some of this gas using quasar absorption lines, seeing shadows where light passes through. But most of it is invisible, too diffuse to detect directly. There might also be dark matter filaments, rivers of dark matter flowing along the web. We can't see dark matter, but we can infer its presence from gravitational lensing, from the bending of light around massive structures. And what we find is that dark matter traces the cosmic web, forming a scaffolding on which galaxies grow. In a sense, we see only the foam on the waves. The real ocean, the dark matter and dark energy, is invisible. We're mapping shadows, inferring a structure we can't directly observe. And yet, we're succeeding. We're piecing together a picture of the universe on the largest scales, and it's beautiful. Here's a mystery closer to home: the dynamo problem. Earth's magnetic field protects us from solar wind, from cosmic rays, from radiation that would strip away our atmosphere and sterilize the surface. Without it, Earth might be like Mars, cold, dry, dead. The field is generated by convection in Earth's outer core, liquid iron flowing, creating electric currents, which generate magnetic fields, which twist and amplify through feedback. It's a dynamo, self-sustaining, powered by heat from the interior. But the details are complicated. The flow in the core is turbulent, three-dimensional, time-varying. It's governed by magnetohydrodynamics, the interaction of fluid flow and magnetic fields, one of the most complex branches of physics. We can't solve the equations exactly. We have to simulate them on supercomputers, and even then, we can only approximate. And Earth's magnetic field does strange things. It flips. Every few 100,000 years, north becomes south, south becomes north. The flips aren't regular. Sometimes they're quick, taking a few thousand years. Sometimes they're slow. Sometimes there are false starts, excursions where the field weakens but doesn't fully flip. The last flip was 780,000 years ago. We're overdue. The field has been weakening for the past 2,000 years, especially over the South Atlantic, where there's an anomaly, a region where the field is unusually weak. Is this the start of a flip? Are we living through the early stages of a magnetic reversal? Probably not. The field fluctuates naturally. The South Atlantic anomaly has existed for centuries, maybe longer. It's not necessarily a precursor to a flip, but it could be. We don't know. If a flip happens, what would we experience? During a flip, the field weakens, perhaps dropping to 1/10 of its current strength. This exposes the surface to more radiation, more cosmic rays. Satellites would be more vulnerable. Power grids might be disrupted by solar storms, but life would survive. The atmosphere provides some protection, and flips have happened hundreds of times in Earth's history without causing mass extinctions. Still, it's unsettling. We depend on the magnetic field, and we don't fully understand it. We can't predict when it'll flip, how fast the flip will occur, or what the consequences will be. We're at the mercy of processes in Earth's core that we can barely observe, let alone control. And other planets have their own magnetic mysteries. Jupiter's field is immensely strong, 20,000 times stronger than Earth's. It's generated by convection in metallic hydrogen, a phase of hydrogen that exists only under extreme pressure, deep in Jupiter's interior. We've never seen metallic hydrogen in a lab. We're not even sure how it behaves, but it's there, generating a field that dominates Jupiter's magnetosphere, stretching millions of kilometers into space. Mercury has a weak field, too weak for its size. Venus has almost no field. Mars had a field but lost it billions of years ago, and its atmosphere was stripped away by solar wind. The Moon once had a field, early in its history, but it's gone now. Why do some planets have fields and others don't? It depends on the interior structure, on whether there's a liquid conducting layer undergoing convection. But the details are murky. We're still figuring out what happens inside planets, what drives their magnetic fields, what determines their fates. Let me tell you about cosmic strings. They're hypothetical defects in space-time, one-dimensional structures formed during phase transitions in the early universe. Think of them as cracks, scars left behind as the universe cooled and symmetries broke. Cosmic strings would be incredibly thin, about the Planck length in diameter, but incredibly massive with tensions around 10 to 21 kilograms per meter. A piece of cosmic string the length of a proton would weigh as much as Mount Everest. And they'd be long, stretching across the universe, perhaps infinite. If cosmic strings exist, they'd have observable effects. They'd create gravitational lensing, doubling images of distant galaxies. They'd generate gravitational waves, detectable by pulsar timing arrays. They'd seed structure formation, creating filaments of galaxies. They might even create closed time-like curves, allowing time travel. But we haven't found cosmic strings. Searches have turned up nothing. Either they don't exist, or they're rarer than expected, or we're not looking in the right way. Most models of the early universe don't predict cosmic strings, but some do, especially grand unified theories and string theory. If they exist, cosmic strings would be remnants of the universe's infancy, fossils of conditions we can never recreate. They'd tell us about phase transitions, about symmetries, about physics at energies far beyond the reach of accelerators. They'd be treasure troves of information about the first moments after the Big Bang. Or they might not exist at all. The universe might have cooled smoothly without forming topological defects. The early universe might have been simpler than we think, or more complicated in ways that don't involve cosmic strings. Either way, the search continues. Because if cosmic strings are out there, finding one would be a Nobel Prize-level discovery, a window into physics we can't access any other way. Now let's talk about the horizon problem more deeply. The cosmic microwave background is uniform to within 1 part in 100,000. Every direction looks the same temperature. But according to standard Big Bang cosmology, regions on opposite sides of the sky were never in causal contact. They were too far apart for light to travel between them in the time since the Big Bang. So how did they reach the same temperature? How did they know to be the same? It's like two people on opposite sides of Earth wearing the same outfit without ever communicating. It's too coincidental. Inflation solves this. Before inflation, the universe was tiny, small enough that all regions were in contact. They equilibrated, reaching the same temperature. Then inflation happened, blowing them apart, expanding a tiny patch to become larger than the observable universe. The uniformity we see is a relic of that early contact. But inflation is weird. It requires a field, the inflaton, with very specific properties. And we don't know what the inflaton is. We've looked for it, searched for its particles, its interactions. Nothing. It might be a scalar field like the Higgs. It might be a pseudo-Goldstone boson. It might be something else entirely. And inflation had to start somehow. What triggered it? Quantum fluctuations? A phase transition? Initial conditions? If initial conditions, we've just pushed the problem back. We haven't explained anything. We've replaced why is the universe uniform with why were the initial conditions right for inflation. Some propose eternal inflation, where inflation never fully stops, constantly creating new regions, new universes. But this raises its own problems. Eternal inflation predicts a multiverse, and testing multiverse theories is nearly impossible. We're trapped in one universe. We can't see the others. Alternatives to inflation exist. The ekpyrotic universe, where our Big Bang was a collision between brains in higher dimensional space. Bouncing cosmologies, where the universe contracts, bounces, and expands, cycling eternally. Variable speed of light theories, where light traveled faster in the early universe, allowing distant regions to communicate. None of these alternatives work as well as inflation. They're less predictive, more contrived, harder to test. Inflation is the best theory we have, but it's not perfect. And the horizon problem remains a reminder that the Big Bang isn't the beginning of the story. Something happened before, something that set the stage for everything that followed. Let me close with one final thought. We've covered dozens of paradoxes, dozens of mysteries. The Fermi paradox, the information paradox, the measurement problem, dark matter, dark energy, the arrow of time. Each one is a challenge, a question without a clear answer. But here's what amazes me. We know enough to ask these questions. A century ago, we didn't know about quantum mechanics, about the expanding universe, about black holes. We've learned so much in such a short time. And the paradoxes, the mysteries, they're not signs of failure. They're signs of progress. Every paradox is a gap in our understanding, a place where our theories break down, where reality surprises us. And gaps are opportunities. They're where new ideas emerge, where breakthroughs happen, where paradigms shift. The universe doesn't owe us answers. It doesn't care if we understand it, but it's given us minds capable of asking questions, eyes capable of seeing stars, instruments capable of detecting gravitational waves. It's given us mathematics, logic, curiosity, the ability to wonder. And we're using those gifts. We're exploring, discovering, creating knowledge where none existed before. We're mapping reality one observation at a time, one theory at a time, one breakthrough at a time. The paradoxes will persist. Some might never be solved, but that's okay, because the journey, the process of inquiry, the struggle to understand, that's what makes us human. That's what gives life meaning. We're a species that looks up at the night sky and asks why. And that, more than anything, is what defines us. So keep wondering, keep asking, keep pushing against the boundaries of knowledge. Because out there, in the cosmos, in the quantum foam, in the singularities and horizons and wave functions, are answers we haven't found yet. And maybe, just maybe, you'll be the one to find them. The universe is waiting. The paradoxes are calling. And the greatest discoveries of all time are still ahead of us, waiting for minds brave enough, curious enough, stubborn enough to seek them out. This is COSM Hush, reminding you that reality is stranger than you think. And that's exactly why it's worth exploring.